Space is full of mysteries. Despite all our scientific advances, the cosmos continues to surprise us. From bizarre objects like magnetars and quasars to unexplained structures spanning billions of light years, our universe is stranger than we ever imagined. Join us as we dive into the many mysteries of our unusual universe. The Great Attractor is a mysterious and massive region of space that exerts a gravitational force strong enough to influence the motion of galaxy clusters, including our own Milky Way. This anomaly lies roughly 150 million light-years away from Earth in the direction of the Centaurus and Norma clusters. Unlike a single, visible object, the Great Attractor represents a gravitational field influencing an extensive swathe of the universe. This immense gravitational pull is attributed to the presence of a concentrated mass of galaxies and dark matter. Dark matter remains largely undetectable because it does not emit, absorb, or reflect light, making its presence known solely through gravitational effects on visible matter. As a result, the Great Attractor continually draws galaxies towards it, including our home galaxy, which travels at an astonishing speed of about 600 kilometers per second towards this cosmic rendezvous. Studies using advanced telescopes and cosmic microwave background radiation have provided insights into this phenomenon. This research has revealed that our local group of galaxies is not only influenced by the Great Attractor, but also by even larger structures, like the Shapley supercluster. Such discoveries hint at the vast and interconnected web of matter that forms the large-scale structure of the universe. Astrophysicists continue to map and study these immense structures to better understand the composition and behavior of the universe. The Great Attractor serves as a fascinating example of the gravitational wonders that persist on a cosmic scale, influencing the trajectory and destiny of entire galaxies. The Bootes Void, one of the largest known voids in the universe, is a staggering region in space with a notable scarcity of galaxies. This vast expanse spans approximately 330 million light-years in diameter. Located in the direction of the constellation Bootes, hence its name, it is sometimes referred to as the Great Nothing. The sheer size and emptiness of the Bootes Void have intrigued astronomers since its discovery in the early 1980s. To understand why such voids exist, we need to consider the large-scale structure of the universe, which resembles a cosmic web. This web consists of filaments of galaxies and clusters interconnected by dark matter with vast voids in between. These voids, like Bootes, are not entirely devoid of matter, but have significantly lower densities. Scientists believe the formation of voids is a natural consequence of the gravitational evolution of the universe. As galaxies and matter gravitate towards dense regions due to gravity, they leave behind less dense areas, creating these voids. The Bootes Void, being exceptionally large, suggests it was formed through successive merging of smaller voids over billions of years. This idea aligns with the hierarchical model of cosmic structure formation, where small structures form first and progressively merge to create larger ones. Intriguingly, even within the Bootes Void, there are some galaxies, though they are sparsely scattered compared to other regions. These galaxies might have formed in small, dense pockets of matter that survived the emptying process. The study of voids like Bootes helps astronomers understand galaxy formation and the distribution of dark matter, offering a glimpse into the dynamic and evolving nature of our universe. The space roar, detected by NASA's Arcade mission in 2006, refers to a perplexing and loud background radio signal emanating from the cosmos. Arcade, which stands for Absolute Radiometer for Cosmology, Astrophysics, and Diffuse Emission, was designed to measure the faint cosmic microwave background radiation, the afterglow of the Big Bang. However, what it detected was an unexpected and extraordinarily strong radio emission. Scientists were surprised because this mysterious signal is much louder than all known sources of radio waves in the universe combined, including emissions from distant galaxies and the Milky Way. The space roar far exceeds the levels predicted by cosmological models, leaving researchers puzzled about its origin. Initially, they considered that it might come from early star formation or unknown astrophysical phenomena. There are several hypotheses regarding the source of this cosmic noise. One possibility is that it may be the collective emissions from countless faint distant radio galaxies that are too weak to be detected individually. Another theory suggests it could be a remnant from an era of rapid star formation shortly after the universe's birth. However, these explanations still do not fully account for the signal's intensity, making the space roar one of the most intriguing unsolved mysteries in cosmology. Future missions and more sensitive instruments are being planned to delve deeper into this enigma. By studying the space roar more thoroughly, scientists hope to uncover new insights about the early universe, galaxy formation, and the possible existence of unknown cosmic phenomena. For now, the space roar stands as a testament to the many unanswered questions that still linger in our exploration of the cosmos. NGC 1052 DF2, often simply referred to as DF2, is a dwarf galaxy that has baffled astronomers because it appears to contain little to no dark matter. Dark matter, which does not emit, absorb, or reflect light, makes up a significant portion of the universe's total mass and is crucial in explaining the gravitational forces that govern galaxy dynamics. The discovery of a galaxy seemingly devoid of this mysterious substance challenges our understanding of how galaxies form and evolve. Typically, galaxies are composed of both visible matter, such as stars and gas, and dark matter, which exerts a gravitational influence that holds these galaxies together. However, observations of DF2 reveal that the motions of its stars and star clusters can be explained almost entirely by the visible matter present, without requiring the mass that dark matter would provide. This finding was confirmed using the motions of globular clusters within the galaxy, which showed remarkably low velocities inconsistent with the presence of dark matter. Several hypotheses have been proposed to explain this anomaly. One possibility is that DF2 formed in a region where dark matter density was unusually low, though such scenarios are rare in cosmological models. Another idea is that DF2 might have undergone interactions or collisions with other galaxies or massive structures, stripping it of its dark matter content. Additionally, it could be that we do not completely understand the processes that lead to the varying dark matter to visible matter ratios in different galactic environments. Further studies and observations are required to determine the definitive reason for DF2's unusual composition. The galaxy offers an exciting opportunity for astronomers to test and refine their models of galaxy formation and the role of dark matter. Studying DF2 and similar galaxies could ultimately illuminate new aspects of the complex relationship between visible and invisible matter in the cosmos. Fast radio bursts, or FRBs, are one of the most enigmatic phenomena in the cosmos. These incredibly brief yet extraordinarily powerful pulses of radio waves originate from distant galaxies, often billions of light-years away. Each FRB lasts just a few milliseconds but can emit more energy in that fleeting moment than our sun produces in an entire day. Since their discovery in 2007, scientists have been feverishly searching for an explanation for these mysterious signals. Several theories have been proposed regarding the sources of FRBs. One of the leading candidates is magnetars, which are a type of neutron star with immensely strong magnetic fields. When these magnetic fields undergo sudden shifts or reconnection events, they can release a colossal amount of energy in the form of radio waves, potentially explaining the sheer power and brief duration of FRBs. This theory gained support when a magnetar within our own galaxy produced an FRB-like burst in 2020, indicating that these exotic objects can indeed create fast radio bursts. Another intriguing possibility is that FRBs could arise from the interactions between neutron stars and black holes. When a neutron star gets too close to a black hole or another neutron star, the extreme gravitational forces and high-energy collisions could generate bursts of radio waves. These cosmic interactions would fit the profile of events capable of producing the immense energies observed in FRBs. Some researchers have ventured into even more speculative territory, proposing that FRBs might be signals from advanced extraterrestrial civilizations using powerful radio transmitters. While this idea is far more controversial and lacks concrete evidence, it captivates the imagination and reminds us of the vast unknowns that still pervade our study of the universe. Ongoing and future observations using more advanced radio telescopes aim to pinpoint the precise locations of FRBs and uncover more about their sources. As data accumulates, the mystery of fast radio bursts may eventually unravel, shedding light on the powerful processes lurking in the depths of space. The unusual motion of stars at the edge of our galaxy, the Milky Way, challenged astronomers for quite some time until the concept of dark matter was proposed. In the early 20th century, observations showed that stars in the outer regions of spiral galaxies, including the Milky Way, were moving much faster than expected based on the visible matter alone. According to Newtonian mechanics, the gravitational pull from observable matter, like stars and gas, should cause orbital speeds to decrease with distance from the galactic center. However, this was not the case. In the 1930s, Swiss astronomer Fritz Zwicky noticed similar discrepancies while studying the Coma cluster of galaxies. He suggested the existence of an unseen mass, which he termed dark matter, to account for the extra gravitational forces needed to explain these high velocities. This idea was later reinforced by American astronomer Vera Rubin's groundbreaking work in the 1970s, which examined the rotation curves of galaxies. Rubin's research provided compelling evidence that dark matter was necessary to explain the anomalous stellar motions at the outskirts of galaxies. Dark matter is believed to make up about 85% of the total mass of the universe, yet it remains invisible because it does not emit, absorb, or reflect light. Its presence is inferred through gravitational effects that are observable at galactic and larger cosmic scales. The outer stars in the Milky Way, therefore, are moving faster because they are influenced by this massive invisible halo of dark matter enveloping the galaxy, contributing substantially to its overall gravitational field. While the exact nature of dark matter remains one of the most profound mysteries in modern astrophysics, numerous experiments and observations are ongoing to detect and understand it better. Theoretical models, computer simulations, and advances in particle physics continue to refine our knowledge about dark matter, bringing us closer to unraveling its elusive properties and role in the cosmos. Tabby's star, also known as KIC 8462852, has captivated astronomers and the public alike due to its erratic and unpredictable dimming events. Discovered through data from the Kepler Space Telescope, this star, located approximately 1,400 light-years away in the constellation Cygnus, exhibits irregular and substantial drops in brightness that defy straightforward explanation. One of the more mundane hypotheses is that a large swarm of comets or a cloud of dust and debris in orbit around the star could be responsible. The idea is that fragments from a disrupted comet or a group of comets could form a dense, irregular pattern of occultation, causing the observed dimming as they pass in front of the star. However, this scenario has limitations, as it requires a very specific and unlikely set of conditions to be plausible. Another possibility involves the presence of an interstellar cloud of dust between Earth and Tabby's star. This interstellar dust could intermittently block the light, leading to the star's observed dimming patterns. However, studies using various wavelengths of light, including infrared, have not found definitive evidence to support this hypothesis. Interstellar dust would typically produce a different dimming pattern across multiple wavelengths, which has not been observed in this case. More exotic theories include the presence of a Dyson sphere or other large structures built by an advanced extraterrestrial civilization, which could potentially obstruct the star's light. However, this explanation remains speculative and lacks empirical support. Searches for technosignatures, such as radio signals typically associated with intelligent life, have so far come up empty. The true cause of Tabby's star's dimming remains an open question. Ongoing observations and future missions hope to gather more data and provide additional insights. Further studies and observations are required to determine the definitive reason for DF2's unusual composition. The galaxy offers an exciting opportunity for astronomers to test and refine their models of galaxy formation and the role of dark matter. Studying DF2 and similar galaxies could ultimately illuminate new aspects of the complex relationship between visible and invisible matter in the cosmos. Fast radio bursts, or FRBs, are one of the most enigmatic phenomena in the cosmos. These incredibly brief yet extraordinarily powerful pulses of radio waves originate from distant galaxies, often billions of light-years away. Each FRB lasts just a few milliseconds but can emit more energy in that fleeting moment than our sun produces in an entire day. Since their discovery in 2007, scientists have been feverishly searching for an explanation for these mysterious signals. Several theories have been proposed regarding the sources of FRBs. One of the leading candidates is magnetars, which are a type of neutron star with immensely strong magnetic fields. When these magnetic fields undergo sudden shifts or reconnection events, they can release a colossal amount of energy in the form of radio waves, potentially explaining the sheer power and brief duration of FRBs. This theory gained support when a magnetar within our own galaxy produced an FRB-like burst in 2020. indicating that these exotic objects can indeed create fast radio bursts. Another intriguing possibility is that FRBs could arise from the interactions between neutron stars and black holes. When a neutron star gets too close to a black hole or another neutron star, the extreme gravitational forces and high-energy collisions could generate bursts of radio waves. These cosmic interactions would fit the profile of events capable of producing the immense energies observed in FRBs. Some researchers have ventured into even more speculative territory, proposing that FRBs might be signals from advanced extraterrestrial civilizations using powerful radio transmitters. While this idea is far more controversial and lacks concrete evidence, it captivates the imagination and reminds us of the vast unknowns that still pervade our study of the universe. Ongoing and future observations using more advanced radio telescopes aim to pinpoint the precise locations of FRBs and uncover more about their sources. As data accumulates, the mystery of fast radio bursts may eventually unravel, shedding light on the powerful processes lurking in the depths of space. The unusual motion of stars at the edge of our galaxy, the Milky Way, challenged astronomers for quite some time until the concept of dark matter was proposed. In the early 20th century, observations showed that stars in the outer regions of spiral galaxies, including the Milky Way, were moving much faster than expected based on the visible matter alone. According to Newtonian mechanics, the gravitational pull from observable matter, like stars and gas, should cause orbital speeds to decrease with distance from the galactic center. However, this was not the case. In the 1930s, Swiss astronomer Fritz Zwicky noticed similar discrepancies while studying the Coma cluster of galaxies. He suggested the existence of an unseen mass, which he termed dark matter, to account for the extra gravitational forces needed to explain these high velocities. This idea was later reinforced by American astronomer Vera Rubin's groundbreaking work in the 1970s, which examined the rotation curves of galaxies. Rubin's research provided compelling evidence that dark matter was necessary to explain the anomalous stellar motions at the outskirts of galaxies. Dark matter is believed to make up about 85% of the total mass of the universe, yet it remains invisible because it does not emit, absorb, or reflect light. Its presence is inferred through gravitational effects that are observable at galactic and larger cosmic scales. The outer stars in the Milky Way, therefore, are moving faster because they are influenced by this massive invisible halo of dark matter enveloping the galaxy, contributing substantially to its overall gravitational field. While the exact nature of dark matter remains one of the most profound mysteries in modern astrophysics, numerous experiments and observations are ongoing to detect and understand it better. Theoretical models, computer simulations, and advances in particle physics continue to refine our knowledge about dark matter, bringing us closer to unraveling its elusive properties and role in the cosmos. Tabby's star, also known as KIC 8462852, has captivated astronomers and the public alike due to its erratic and unpredictable dimming events. Discovered through data from the Kepler Space Telescope, this star, located approximately 1,400 light-years away in the constellation Cygnus, exhibits irregular and substantial drops in brightness that defy straightforward explanation. One of the more mundane hypotheses is that a large swarm of comets or a cloud of dust and debris in orbit around the star could be responsible. The idea is that fragments from a disrupted comet or a group of comets could form a dense, irregular pattern of occultation, causing the observed dimming as they pass in front of the star. However, this scenario has limitations, as it requires a very specific and unlikely set of conditions to be plausible. Another possibility involves the presence of an interstellar cloud of dust between Earth and Tabby's star. This interstellar dust could intermittently block the light, leading to the star's observed dimming patterns. However, studies using various wavelengths of light, including infrared, have not found definitive evidence to support this hypothesis. Interstellar dust would typically produce a different dimming pattern across multiple wavelengths, which has not been observed in this case. More exotic theories include the presence of a Dyson sphere or other large structures built by an advanced extraterrestrial civilization, which could potentially obstruct the star's light. However, this explanation remains speculative and lacks empirical support. Searches for technosignatures, such as radio signals typically associated with intelligent life, have so far come up empty. The true cause of Tabby's star's dimming remains an open question. Ongoing observations and future missions hope to gather more data and provide additional insights. By continuing to monitor and study this star, astronomers aim to unlock the secrets behind its strange behavior and possibly discover new astrophysical phenomena in the process. The universe's apparent faster-than-expected expansion is primarily attributed to the enigmatic force known as dark energy. This phenomenon was first discovered in the late 1990s when astronomers studying distant supernovae found that these cosmic explosions were dimmer and therefore farther away than expected. This suggested that the universe's expansion wasn't slowing down under gravity, as once thought, but accelerating. Dark energy is hypothesized to make up about 70% of the universe. It acts like a repulsive force, counteracting gravity and driving the acceleration of the universe's expansion. However, its exact nature remains one of the greatest mysteries in cosmology. One idea is that dark energy could be a property of space itself, described by the cosmological constant in Einstein's equations of general relativity. This constant represents a fixed energy density filling space uniformly. Beyond the cosmological constant, other theories propose dynamic forms of dark energy, often termed quintessence, which could vary over time and space. These theories suggest dark energy might be a field that evolved differently during various phases of the universe's history. Understanding which, if any of these models is correct, requires more precise measurements of the universe's expansion rate and the distribution of galaxies and cosmic structures. Moreover, the discrepancy often highlighted involves the Hubble constant, which measures the universe's rate of expansion. Two primary methods for determining this constant, one using the cosmic microwave background radiation and model predictions, and the other using observable supernovae and galaxy movement, yield slightly different results. This inconsistency has prompted scientists to delve deeper into the methods and underlying physics to see if new physics or overlooked factors might be at play. The study of dark energy and the universe's accelerated expansion continues to be a major focus of astrophysical research. Instruments like the Hubble Space Telescope, the upcoming James Webb Space Telescope, and ground-based observatories are designed to gather more data to help resolve these cosmic enigmas. As our understanding improves, we hope to uncover the true nature of dark energy and gain deeper insights into the fundamental workings of the universe. The star HD 139139, also nicknamed Random Transitor, has intrigued astronomers due to the bizarre and unexplained transit events observed around it. Located about 350 light-years away in the constellation Libra, HD 139139 exhibits an extraordinary pattern of dimming that does not conform to any known natural phenomena. This irregularity was discovered using data from the Kepler Space Telescope. Typically, transits of planets across a star lead to regular periodic dips in brightness as the planet passes between the star and our line of sight. However, the dimming events observed around HD 139139 are highly unpredictable, with no discernible periodicity. These events occur with varying depths and durations, adding layers of complexity to the mystery. Several hypotheses have been proposed to explain this phenomenon. One possibility is the presence of a large group of disintegrating planets or planetesimals. As these objects break apart, their debris could lead to irregular and inconsistent transits. Although conceivable, this scenario requires a highly specific and unusual set of circumstances to explain the observed behavior fully. Another idea involves the presence of a complex ring system or large clouds of dust and debris around the star. These elements, if in chaotic orbits, could account for the inconsistent transit patterns. However, for such a dust cloud or debris field to exist and remain stable in such a manner raises further questions about the mechanics and composition of the system. Despite the allure of extraterrestrial explanations, such as artificial megastructures or engineered swarms of satellites, these remain purely speculative and unsubstantiated by current evidence. Advanced civilizations constructing large-scale structures around stars would be an extraordinary claim requiring equally extraordinary proof, which we currently do not possess. The data from HD 139139 continue to puzzle astronomers and drive efforts to gather more observations and apply new models. Future studies using more sophisticated tools and methods may eventually clarify the nature of the strange objects orbiting this star, potentially revealing new insights into stellar and planetary systems. Hypervelocity stars traveling at speeds exceeding the escape velocity of our galaxy are fascinating phenomena that challenge our understanding of stellar dynamics. These stars, moving at several hundred kilometers per second, are essentially on a one-way journey out of the Milky Way. The primary explanation for their incredible speeds involves interactions with supermassive black holes, such as Sagittarius A star, located at the center of our galaxy. The most widely accepted mechanism for creating hypervelocity stars is the so-called Hills mechanism, named after astronomer Jack Hills, who first proposed it in the 1980s. According to this theory, binary star systems that venture too close to a supermassive black hole can be disrupted by its intense gravitational field. In such a scenario, the black hole can capture one of the stars while flinging the other out at tremendous speeds. This catapult-like effect sends the ejected star hurtling through space at velocities sufficient to escape the gravitational pull of the Milky Way. Another potential source of hypervelocity stars could involve interactions within densely packed star clusters. In these environments, close encounters between multiple stars and compact objects like black holes or neutron stars can also result in one of the stars being ejected at high velocity. These gravitational slingshots are less common but still contribute to the population of hypervelocity stars. Recent discoveries have expanded our understanding of hypervelocity stars, suggesting some may even originate from other galaxies, particularly if they were initially accelerated by the gravitational forces of another nearby supermassive black hole and later captured by the Milky Way's gravitational field. This possibility adds an intriguing layer to the story, indicating that hypervelocity stars can traverse vast intergalactic distances. Ongoing research and observations aim to track and study these high-speed stars more closely. By doing so, scientists hope to learn more about the dynamic processes at the centers of galaxies, the properties of supermassive black holes, and the history of stellar interactions across cosmic scales. Hypervelocity stars not only exemplify the dynamic and sometimes violent nature of our cosmos, but also serve as excellent probes into the gravitational and astrophysical forces governing our universe. The antimatter fountains are a vital area of exploration in astrophysics, helping us understand high-energy processes and cosmic particle interactions. Continued observations and more sophisticated models are essential to refining our understanding of the numerous factors contributing to these fascinating phenomena. By delving deeper into the nature of the gamma-ray emissions and their underlying sources, scientists hope to unlock more secrets of the dynamic environment at the center of our galaxy. Free-floating planets, also known as rogue planets, are planetary mass objects that drift through the galaxy untethered to any star. The discovery of these lone wanderers has opened a fascinating chapter in our understanding of planetary formation and galactic dynamics. Their presence is primarily explained through several main mechanisms. One prominent theory suggests that free-floating planets were initially born in planetary systems much like those of our own solar system. During the early chaotic stages of planetary formation, gravitational interactions between planets and other massive bodies can be quite tumultuous. These interactions, especially those involving large gas giants, can result in some planets being ejected from their parent star's gravitational influence. This ejection process can be so violent that the planet is flung into interstellar space with enough velocity to escape its solar system entirely. Another possibility is that some free-floating planets could have formed directly from the collapse of gas clouds, similar to the way stars form, but on a smaller scale. In regions of space where gas and dust are abundant, smaller clumps might coalesce under gravity to form planet-sized objects without ever becoming part of a stellar system. This pathway suggests a kind of starless planet formation, which, while less common, could contribute to the population of rogue planets. The discovery of these planets has been facilitated by techniques such as gravitational microlensing. When a free-floating planet passes in front of a distant star, its gravitational field can bend and magnify the light from that star, creating a detectable signal. This method allows astronomers to infer the presence of the planet despite it not emitting light of its own or being in the vicinity of a bright host star. Further research and observation continue to uncover more about these mysterious travelers. Missions like NASA's upcoming Nancy Grace Roman Space Telescope aim to widen the search and increase our ability to detect and study free-floating planets. By understanding how these planets form and survive, scientists hope to gain insights into the broader processes of planetary system dynamics and galaxy evolution, shedding light on the diverse ways planets can exist and interact within the cosmos. Ultra-high-energy cosmic rays are like ghostly bullets from the edge of the universe, with speeds and energies that boggle the mind. These particles travel at nearly the speed of light and possess energies far exceeding those produced by any human-made particle accelerator. Pinpointing their origins requires delving into the most extreme environments known to science. One leading process thought to create these cosmic rays involves active galactic nuclei. At the heart of certain galaxies lie supermassive black holes, often surrounded by swirling disks of gas and dust. As material in these disks spirals into the black hole, immense amounts of energy are released, forming jets that shoot out at nearly light speed. These jets are powerful enough to accelerate particles to ultra-high energies, flinging them across the cosmos. Another possible source is the chaotic aftermath of supernovae, or even more dramatically, gamma-ray bursts. When massive stars explode as supernovae or collide to form gamma-ray bursts, they release unimaginable amounts of energy in short, powerful pulses. These events create shockwaves that can propel particles to extraordinary velocities, launching them far beyond the confines of their home galaxies. Then there are the mysterious interactions involving dark matter or hypothetical phenomena like cosmic strings. Some theories suggest that collisions or decay of these elusive entities could also spawn ultra-high-energy cosmic rays. However, these ideas remain largely speculative and drive physicists to continue searching for clues in the cosmic puzzle. Each of these potential processes speaks to the incredible forces at play in our universe, forces that challenge and inspire our understanding while pushing the boundaries of what seems possible. Stars like R136A1, which are born with masses over 300 times that of our Sun, are truly cosmic behemoths. The process of their formation is a dazzling ballet of gas, gravity, and time set against the dark backdrop of space. To understand how these towering giants come into being, we need to look at the environments where stars form, as well as the physics governing this grand spectacle. Such massive stars usually emerge within dense, vibrant regions known as stellar nurseries. These regions, packed with gas and dust, are called giant molecular clouds. Within these clouds, small pockets of gas can become gravitationally unstable, causing them to collapse under their own weight. As they collapse, they heat up and the pressure increases, igniting nuclear fusion, the hallmark of starbirth. In the case of R136A1 and its monstrous siblings, these stars likely formed within particularly large and dense molecular clouds. The extreme mass is gathered by rapid and efficient accretion of gas from their environment. Because these clouds contain colossal amounts of material, the stars that form within them can accrue tremendous masses before the intense radiation pressure from their surfaces blows away the surrounding gas, a process known as radiation-driven mass loss. Furthermore, during their early stages, some massive stars may also form through the merging of smaller stars. In dense star clusters, such interactions are not uncommon. The gravitational dance of close and massive companions can lead to collisions and mergers, creating even larger stars. R136A1, residing in the dense core of the Tarantula Nebula's star cluster, might have grown through such dynamic interactions, accumulating more mass each time. The formation and growth of stars, such as R136A1, reveal the amazing capabilities of nature in shaping objects that stretch the limits of our understanding, painting a vivid portrait of the extreme conditions that characterize our universe's most colossal phenomena. The intriguing Fermi bubbles are colossal gamma-ray emitting structures extending above and below the plane of the Milky Way. Spanning roughly 25,000 light-years each, these bubbles were first discovered by the Fermi Gamma-Ray Space Telescope in 2010, sparking curiosity and debate about their origins. One prevailing theory suggests that the Fermi bubbles result from intense activity at the center of our galaxy, specifically around its supermassive black hole, Sagittarius A star. In the distant past, Sagittarius A star might have undergone a period of aggressive feeding, devouring vast amounts of gas and debris. When material falls into a black hole, not all of it gets swallowed. Some is expelled in powerful jets. These jets, brimming with high-energy particles, could have inflated the bubbles, creating the magnificent structures we observe today. Another fascinating idea proposes that the Fermi bubbles were produced by a series of massive starburst events. In these starbursts, clusters of massive stars rapidly formed and exploded as supernovae over a short period. These explosive events would collectively generate enough energy to drive hot gas out from the center of the galaxy, forming the expansive bubbles. The supernova-generated shockwaves and winds from dying stars could provide the necessary oomph to inflate these giant structures. Further supporting these theories are the X-ray observations of the bubble's edges, which suggest they are filled with extremely hot gas. This hot gas, likely energized by the mechanisms of either black hole activity or starbursts, glows brightly in gamma-ray light due to its interactions with surrounding matter and magnetic fields. Unlocking the true nature of the Fermi bubbles requires piecing together clues from gamma-ray and X-ray observations, coupled with advanced simulations of galactic dynamics. These enigmatic bubbles serve as a testament to the energetic processes that can occur in the hearts of galaxies, offering insight into the dynamic and explosive history of our very own Milky Way. Quark stars, if they exist, represent an even more exotic state of matter than neutron stars. Both of these celestial objects are the remnants of massive stars that have gone supernova, but the differences lie in the nature of the matter they contain and the conditions within their cores. Neutron stars are formed when a star with a mass greater than that of the Sun exhausts its nuclear fuel and undergoes a supernova explosion. The core of the star collapses under gravity, compressing protons and electrons together to form neutrons. The result is an incredibly dense object where the matter exists in a state known as neutron degenerate matter. Neutron stars typically have a radius of about 12 miles, but can contain up to twice the mass of our Sun. Quark stars are hypothesized to take this process of collapse even further. In a quark star, the pressure at the core is so extreme that neutrons themselves break down into their constituent quarks. These free quarks, primarily up and down quarks, form a new state of matter called quark degenerate matter. The density of a quark star would surpass that of a neutron star, potentially leading to a smaller radius for a given mass. If quark stars exist, they might be identified by their exceptionally high densities and distinctive behaviors. For instance, quark stars could be able to sustain stronger magnetic fields and might exhibit different cooling patterns compared to neutron stars due to the unique properties of quark matter. Observations of objects that seem too compact to be neutron stars, but not collapsed entirely into black holes, could hint at the existence of quark stars. Confirming the existence of quark stars poses significant challenges, as the differences between neutron stars and quark stars manifest under conditions that are incredibly difficult to observe directly. Advanced telescopes and future space missions may provide the crucial data needed to determine whether these extraordinary objects populate our universe, pushing the boundaries of our understanding of matter in its most extreme forms. Strange matter is an even more exotic and theoretical state of matter thought to exist under extreme pressures and densities. It consists not just of the usual up and down quarks found in protons and neutrons, but also a third type, the strange quark. When strange quarks combine with up and down quarks, they form particles known as strangelets. These strangelets could combine to create a new, stable form of matter fundamentally different from anything we see in everyday life. Strange stars, if they exist, would be composed predominantly of this strange matter. The formation of a strange star could occur in a manner similar to that of neutron stars. When a massive star undergoes a supernova, its core collapses under gravity to create extremely high pressures and densities. If these conditions are sufficient to force neutrons to break down into quarks, and if strange quarks then form and stabilize within this environment, the result would be a strange star. One of the most intriguing aspects of strange matter is its potential absolute stability. Some theories suggest that strange matter might be more stable than ordinary nuclear matter. This stability implies that if strange matter were to come into contact with ordinary matter, it could, in theory, convert the ordinary matter into more strange matter, a process called strange matter infection. However, this remains purely theoretical and highly speculative. The properties of strange stars would likely distinguish them from neutron stars. They could be denser and more compact, with potentially smaller radii for a given mass. Their composition might result in different thermal and magnetic properties and unique surface phenomena. Additionally, strange stars would probably emit distinctive radiation signatures that could one day be detected by our most advanced observatories, providing a tantalizing piece of evidence for their existence. As we reach further into the cosmos with our telescopic eyes, these extraordinary objects beckon us to explore deeper into the quantum realm, challenging our comprehension of the universe's most extreme and exotic forms of matter. Hypervelocity stars are extraordinary objects that have been ejected from their home galaxies at speeds so great they can escape the gravitational pull of the galaxy itself. The existence of these stars, which can travel at several million miles per hour, raises fascinating questions about the violent and complex processes occurring in the cosmos. One compelling explanation for the creation of hypervelocity stars involves interactions with supermassive black holes. In a binary star system where two stars orbit each other, if this system drifts too close to the supermassive black hole at the galaxy's center, the intense gravitational forces can rip the pair apart. One star might be captured by the black hole, while the other is flung away at incredible speeds, a phenomenon known as the Hill's mechanism. Another scenario involves three-body interactions between stars. In densely populated star clusters, close encounters between stars can result in one star gaining enough kinetic energy to be expelled from the system entirely. These interactions are more probable in regions where stars are packed tightly together, resulting in some stars being hurled out into intergalactic space. Additionally, supernova events can create hypervelocity stars. In a binary system, if one star explodes as a supernova, the sudden loss of mass can drastically change the gravitational dynamics. The surviving star can be propelled away at high speeds due to the altered gravitational forces, sending it hurtling out of its galaxy. These ejection processes not only paint a picture of the tumultuous environments that stars can sometimes find themselves in, but also highlight the immense gravitational and energetic forces at play in our universe. By studying hypervelocity stars, astronomers gain invaluable insights into the extreme conditions and dynamic processes that shape the galaxies, offering a glimpse into the cosmic dance of gravity and motion on a grand scale. The cosmic web is an intricate, large-scale structure that forms the backbone of our universe, connecting galaxies across immense voids through filaments of dark matter and gas. This web-like arrangement of matter is not only captivating in its appearance, but also fundamental to our understanding of the universe's large-scale structure and evolution. The cosmic web emerged from the tiny fluctuations in the density of matter present in the early universe, just after the Big Bang. These fluctuations grew under the influence of gravity, with regions slightly denser than their surroundings attracting more matter, eventually forming the large-scale structures we observe today. Dark matter, which does not emit or absorb light but exerts gravitational forces, played a crucial role in this process. It acted as the scaffolding for the formation of galaxies and galaxy clusters, guiding the distribution of ordinary matter. The filaments of the cosmic web are composed predominantly of dark matter, but also contain a significant amount of hot, ionized gas. Galaxies and galaxy clusters form at the intersection of these filaments, where the density of matter is highest. The web's nodes are typically populated by superclusters of galaxies, while the filaments themselves can stretch for hundreds of millions of light-years, threading through the cosmos from one galactic congregation to another. The cosmic web's true nature is revealed through various observational techniques, such as gravitational lensing, which allows astronomers to infer the presence and distribution of dark matter by studying how it bends the light from distant objects. Additionally, large-scale galaxy surveys and detailed computer simulations help map out this vast network, providing a visual and analytical representation of its structure. Understanding the cosmic web is crucial as it influences the dynamics and evolution of galaxies. It governs the flow of gas into galaxies, fueling star formation, and the growth of supermassive black holes. This vast interconnected framework not only shapes the universe on the largest scales, but also sets the stage for the intricate dance of cosmic structures over billions of years, offering a grand perspective on our place in the cosmos. The apparent alignment of quasars across vast cosmic distances is one of the more intriguing and puzzling discoveries in astrophysics. These supermassive black holes at the centers of young galaxies are among the brightest objects in the universe, releasing enormous amounts of energy as they gobble up surrounding material. The observed alignment of their polarizations, a measure of the light's orientation, suggests a level of coherence over distances of billions of light-years, challenging our understanding of the universe's large-scale structure. One hypothesis is that these alignments may trace back to the influence of the large-scale structure of the universe itself, the cosmic web. The filaments of dark matter and gas stretching across the cosmos could impart a degree of coherence to the regions where quasars form. Essentially, the quasi-linear structures of the cosmic web might influence the angular momentum of the matter funneling into the supermassive black holes, aligning the jets of the resulting quasars along preferred directions. Another possibility involves the role of primordial magnetic fields. If large-scale magnetic fields were woven into the fabric of the early universe, they could have left an imprint on the orientation of quasars. These magnetic fields might stretch across intergalactic distances, guiding the alignment of quasar jets and their associated polarized light. Although these primordial magnetic fields are not fully understood, they offer a tantalizing avenue for further exploration. The alignments could also be a statistical anomaly, a coincidence that appears meaningful but results from the random orientations of quasar jets combined with the way we observe them. However, the sheer scale and coherence of these observed alignments make this explanation less likely, prompting astronomers to seek more substantive causes. Ultimately, explaining the alignment of quasars requires diving deeper into both observational data and theoretical models. Future observations with more sensitive instruments, alongside sophisticated simulations of cosmic evolution, might unravel this mystery, shedding light on the interplay between cosmic forces and the extreme environments of quasars. Each clue we uncover brings us closer to understanding the universe's grand design and the forces that govern its most luminous and enigmatic objects. The Fingers of God effect is a peculiar phenomenon observed in galaxy surveys, where galaxies appear elongated or stretched along the line of sight, forming what resembles spectral fingers pointing towards us. This effect is not a true physical elongation, but rather a result of peculiar velocities and the way we measure distances in the universe. To understand this effect, we need to consider how galaxy distances are determined. One way to measure a galaxy's distance is through its redshift, the stretching of light to longer wavelengths due to the expansion of the universe. However, this redshift includes not only the expansion of space itself, but also the galaxy's peculiar velocity, which is its motion relative to the overall cosmic flow. Galaxies in clusters move under the local gravitational influences of their peers and can have significant velocities in various directions. When galaxies in a cluster move towards or away from us, their peculiar velocities add to or subtract from the redshift caused by the universe's expansion. If we assume that the redshift directly translates into distance, galaxies with higher peculiar velocities appear shifted from their true positions along our line of sight, creating the elongated appearance. Thus, clusters of galaxies which are dense with many interacting galaxies exhibit these fingers pointing radially towards us. This effect gives valuable insights into the dynamics within galaxy clusters. By studying the fingers of God, astronomers can infer the velocity dispersions of galaxies in clusters, providing clues about the gravitational interactions and the total mass, including dark matter, within these clusters. It underscores the importance of peculiar velocities in understanding the large-scale structure of the universe and the interactions that shape individual galaxies' positions and movements. Correcting for the fingers of God involves disentangling the contribution of peculiar velocities from the overall redshift. Advanced methods and models refine our understanding of the true distribution of galaxies, painting a more accurate picture of the cosmic landscape and revealing the underlying structures that govern the universe's grand architecture. Cosmic voids and supervoids are vast empty spaces between the filaments of matter in the cosmic web, where galaxies are sparse or almost entirely absent. They are intriguing structures that result from the universe's violent dance of gravity and expansion, and play a crucial role in our understanding of cosmology and the universe's evolution. The formation of these voids begins in the early universe, shortly after the Big Bang. Initial density fluctuations present in the primordial soup of particles and radiation cause some regions to be denser than others. Over time, gravity pulled matter into these denser regions, which eventually became the galaxies, galaxy clusters, and the intricate filaments of the cosmic web we observe today. Consequently, less dense regions were left behind, forming the cosmic voids and supervoids. As the universe expanded, these voids grew larger. The matter within them continued to move towards the denser regions, effectively draining the voids and making them even emptier over billions of years. Some voids have grown to immense sizes, spanning tens to hundreds of millions of light years across, making them some of the largest known structures in the universe. Cosmic voids and supervoids are significant for several reasons. First, they provide a unique environment to test theories of cosmic evolution and the large-scale structure of the universe. Their relative emptiness allows astronomers to examine the effects of dark energy, which is driving the accelerated expansion of the universe, without the interference of gravitational influences from large amounts of mass. Additionally, studying voids helps refine our models of galaxy formation and distribution. The properties of voids, such as their shapes, sizes, and distribution, offer clues about the initial conditions of the universe and the nature of cosmic inflation, the rapid expansion that occurred in the universe's first moments. Lastly, cosmic voids can serve as cosmic laboratories for testing the laws of physics in low-density environments. By observing how light and matter behave in these vast, nearly empty spaces, scientists can explore fundamental questions about the interplay between gravity, dark matter, and dark energy, shedding light on some of the universe's most profound mysteries. Cosmic strings are hypothetical one-dimensional defects in the fabric of space-time, believed to have formed in the early universe shortly after the Big Bang. These intriguing objects are thought to be remnants from phase transitions, much like the formation of cracks in ice as it freezes, but on a cosmic scale. The nature of cosmic strings involves their incredibly thin, yet immensely dense structure. Though they are one-dimensional, meaning they have length but practically no width, They contain mass and energy so concentrated that their gravitational effects can be extraordinary. A cosmic string, if it exists, might be as thin as a proton yet stretch across billions of light years, making them truly colossal and slender phenomena in the cosmos. The formation of cosmic strings is tied to the cooling and expansion of the universe. As the universe cooled after the Big Bang, it underwent several phase transitions. During these transitions, the symmetry of the fundamental forces may have changed, leading to the formation of topological defects like cosmic strings. These strings could be viewed as remnants of the universe's early symmetry breaking, akin to the way defects appear in crystals as they cool and solidify. The theoretical significance of cosmic strings lies in their potential effects on the universe's evolution and structure. Cosmic strings could provide insights into the fundamental physics of the early universe, including the nature of the forces and particles that existed shortly after the Big Bang. Their gravitational influence could create distinct patterns in the cosmic microwave background radiation, leaving imprints that we might detect with sensitive observations. Furthermore, cosmic strings could play a role in the formation of large-scale structures in the universe by acting as seeds for the gravitational clustering of matter, influencing the distribution of galaxies and galaxy clusters. Observing the gravitational lensing effects caused by cosmic strings could provide evidence for their existence. They are predicted to create distinctive double images of background objects due to their intense gravitational fields. While no direct evidence for cosmic strings has been found yet, their potential discovery could revolutionize our understanding of the universe's birth and the fundamental nature of space-time. As we refine our observational techniques and develop new ways to detect the faint imprints of these enigmatic objects, cosmic strings remain an alluring possibility that could unlock new dimensions of cosmological knowledge. Explaining the apparent periodicity in the distribution of galaxies dives into the realm of cosmic structures and the forces shaping the universe at its largest scales. The periodicity refers to the observation that galaxies seem to cluster in an almost regular wave-like pattern across enormous distances, hinting at an underlying order in the cosmic web. One leading explanation involves the concept of baryon acoustic oscillations, which trace back to the early universe. Shortly after the Big Bang, the universe was a hot, dense plasma of electrons, protons, and photons. During this period, sound waves or acoustic waves propagated through the plasma, driven by the interplay between gravitational attraction and pressure from radiation. These waves created regions of alternating overdensity and underdensity. Around 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral atoms, leading to the decoupling of matter and radiation. This period, known as recombination, left a frozen imprint of the acoustic waves on the distribution of matter. The regions of overdensity evolved into galaxies and clusters of galaxies, while the underdense regions became the cosmic voids. These frozen patterns form a regular repetitive structure, explaining the observed periodicity. Another contributing factor might be the gravitational effects within large-scale structures. The interplay of dark matter, which dominates the universe's mass, and ordinary matter creates gravitational wells that reinforce the clustering of galaxies at specific intervals. Moreover, cosmic inflation, a rapid expansion of the universe in its earliest moments, might have set initial conditions with slight periodic variations in density, which were later amplified by gravitational forces. Furthermore, the presence of dark energy, driving the accelerated expansion of the universe, could influence the apparent periodicity in the distribution of galaxies. Dark energy modifies the rate at which structures grow and evolve over time, potentially enhancing the regular spacing observed in galaxy distributions. Studies of galaxy surveys and the cosmic microwave background radiation provide crucial data for understanding these patterns. The Sloan Digital Sky Survey and other deep field observations map the three-dimensional positions of millions of galaxies, offering a detailed view of the universe's large-scale structure. By analyzing these data, cosmologists refine their models and theories about the processes that shape the cosmic landscape, bringing us closer to unveiling the secrets behind the elegant and periodic distribution of galaxies across the universe. The Great Wall of Sloan, also known as the Sloan Great Wall, is one of the largest known structures in the universe, characterized by its colossal ring-like arrangement of galaxies and galaxy clusters. This structure stretches over 1 billion light-years and provides a stunning example of the cosmic web's intricate architecture. Artur. The formation of such an immense structure is closely tied to the processes that govern the evolution of the universe on the grandest scales. The Great Wall of Sloan arose from the primordial density fluctuations in the early universe. These fluctuations, present in the cosmic microwave background radiation, are the seeds that, under the influence of gravity, grew into the vast structures we observe today. As regions of higher density attracted more matter, they formed filaments and clusters. These filaments intersect in denser nodes, creating superclusters of galaxies connected by relatively thinner threads of matter. The Great Wall of Sloan represents a particularly dense and extended region of this cosmic web, where multiple filaments intersect, forming a vast, coherent structure. In addition to gravity, another key factor in its formation is the role of dark matter and dark energy. Dark matter acts as the scaffolding that shapes the large-scale structure of the universe, guiding the accumulation of ordinary matter into these grand formations. The distribution and interaction of dark matter helped create the dense nodes and elongated filaments. Meanwhile, dark energy influences the overall expansion of the universe, affecting how these structures grow and evolve over cosmic time. The discovery and study of the Sloan Great Wall emerged from data collected by the Sloan Digital Sky Survey, which maps the three-dimensional positions of galaxies across a significant portion of the sky. Analysis of this data revealed the enormous scope and complexity of the structure, showcasing a level of organization and coherence that is both awe-inspiring and a testament to the underlying physical principles shaping the cosmos. The Great Wall of Sloan offers a profound glimpse into the universe's large-scale structure and the forces at play in its formation. By studying such structures, astronomers refine their understanding of the fundamental laws governing cosmic evolution and the intricate dance of matter and energy that shapes the universe. These colossal formations illuminate the interconnectedness of all things in the cosmos, following a pattern laid down in the universe's earliest moments. Galactic filaments are vast, thread-like structures spanning hundreds of millions of light-years, forming the backbone of the cosmic web. They consist of galaxies, gas, and dark matter, weaving through the universe and connecting clusters and superclusters. To understand their formation and evolution, we must delve into the cosmos's earliest moments and the forces shaping its large-scale structure. The genesis of galactic filaments begins shortly after the Big Bang. The early universe was a hot, dense plasma uniform in all directions, but with tiny fluctuations in density. As the universe expanded and cooled, gravity began to amplify these fluctuations, drawing matter into dense regions and creating a more heterogeneous distribution. Dark matter, which makes up about 27% of the universe's mass, plays a crucial role in this process. Dark matter clumps together under the force of gravity, creating a scaffolding for ordinary matter to follow. As the universe evolved, these clumps of dark matter attracted more gas and dust, eventually forming galaxies and galaxy clusters. The filaments of dark matter connected these dense regions, serving as highways along which matter flowed, leading to the formation of the galactic filaments observed today. The intricate dance of gravitational forces continues to shape and refine these structures over billions of years. Galaxies and clusters within the filaments experience complex gravitational interactions, mergers, and accretions, constantly evolving the filament's shapes and compositions. Additionally, cosmic filament growth is influenced by the overall expansion of the universe, driven by dark energy. This expansion stretches the filaments, making them ever longer and more diffuse over time. Observations from large-scale galaxy surveys, such as the Sloan Digital Sky Survey and other deep-field observations, map the three-dimensional positions of galaxies, revealing the vast cosmic tapestry. Computer simulations also play a crucial role in understanding filament formation and evolution. Simulations such as the Millennium Simulation and Illustris simulate the development of cosmic structures from the early universe to the present day, providing a virtual laboratory to study the processes shaping galactic filaments. The study of galactic filaments sheds light on the universe's overall architecture and the complex interplay between dark matter, gravity, and cosmic expansion. These colossal structures are not just cosmic landmarks, but key components in our understanding of galaxy formation, the distribution of matter, and the universe's evolution, revealing the beautiful and intricate design of the cosmos. The cold spot in the cosmic microwave background is an intriguing anomaly that sparks significant interest and debate among cosmologists. This region, located in the southern hemisphere of the sky, is conspicuously cooler than the surrounding areas by about 70 microkelvin. The cold spot was first detected by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite, raising compelling questions about its origin and implications for cosmology. One possibility is that the cold spot arose from random fluctuations in the CMB. The CMB represents the afterglow of the Big Bang, revealing tiny temperature variations imprinted when the universe was just 380,000 years old. These fluctuations are generally well understood as remnants of quantum perturbations stretched to cosmic scales during inflation. However, the cold spot's significant deviation makes purely random origin seem statistically unlikely, suggesting that other factors might be at play. Another hypothesis involves the integrated Sachs-Wolf effect, where the cold spot might be due to the interaction between CMB photons and the gravitational potential of large-scale structures. This effect occurs as light from the CMB travels through cosmic voids. These vast, underdense regions can expand faster under dark energy's influence, altering the energy of passing photons. If the cold spot corresponded to a supervoid along our line of sight, photons passing through it could lose energy, appearing cooler when they reach us. However, even the largest known voids don't seem sufficient to fully explain the cold spot's temperature anomaly. More exotic theories propose that the cold spot could be evidence of phenomena beyond the standard cosmological model, such as a region influenced by another universe in a multiverse scenario. Hypothetically, our universe might have collided with a neighboring universe, creating the cold spot as an imprint of this cosmic interaction. While intriguing, this idea remains speculative and lacks empirical support. The cold spot's significance lies in its potential to challenge and refine our understanding of the universe. Whether it stems from peculiar large-scale structures, unexplained physical processes, or hints at new physics, studying the cold spot helps test the limits of the standard cosmological model. As cosmologists analyze more data and develop advanced theoretical frameworks, the cold spot continues to be a focal point of inquiry, potentially unveiling deeper insights into the universe's fundamental nature. The apparent lack of small satellite galaxies around the Milky Way, often referred to as the missing satellites problem, is a fascinating mystery in modern cosmology. According to simulations based on the current understanding of dark matter and galaxy formation, we should expect to see hundreds, if not thousands, of small satellite galaxies orbiting larger galaxies like the Milky Way. Yet when we observe our cosmic neighborhood, we find significantly fewer. One explanation could be that these satellites are simply very faint and hard to detect with current telescopes. Many of these smaller galaxies contain fewer stars and could be dominated by dark matter, making them almost invisible. Advances in telescope technology, such as the Large Synoptic Survey Telescope, are expected to uncover more of these elusive satellites in the coming years, thereby bridging some of this gap. Another intriguing possibility involves the physics of galaxy formation itself. The formation of stars within these small galaxies may have been inhibited by a variety of factors, such as supernova explosions or the reionization of the universe, which heated and dispersed the gas needed to form new stars. These processes may have stunted the growth of potential satellite galaxies, leaving them too dim or too small to be easily observed today. Lastly, it is possible that our cosmological models need refinement. Current models largely depend on the behavior of dark matter, which remains only indirectly observable. If dark matter behaves differently than our models predict, it could alter our understanding of galaxy formation and evolution, potentially explaining the discrepancy in the number of observed small satellites. As we continue to study this enigmatic component of our universe, our theories will evolve, and with them our comprehension of the cosmos will deepen. In regions of extreme gravity, like those found near black holes, the nature of time becomes profoundly different from our everyday experience. According to Einstein's theory of general relativity, gravity not only affects the motion of objects, but also the fabric of space-time itself. Near a black hole, this effect is particularly intense, leading to some astonishing phenomena. One of the most startling predictions is time dilation. As you approach a black hole, time for you would slow down relative to an observer far away. If you were to hover near the event horizon, the boundary beyond which nothing can escape the black hole's pull, time would appear to nearly stop compared to someone at a safe distance. This means that what might feel like a few minutes near the event horizon could translate to years, or even centuries for someone observing from far away. This effect is a result of the black hole's immense gravitational field warping spacetime. The stronger the gravitational field, the more spacetime is curved and the more time stretches. This time dilation is not just a theoretical concept, it has practical implications. For instance, the incredibly precise timekeeping required for global positioning system satellites must account for the weaker gravitational field experienced in orbit compared to the surface of the Earth. Furthermore, if you ventured beyond the event horizon, traditional concepts of time and space begin to break down entirely. Inside a black hole, the gravitational pull is so extreme that it forces all paths to converge towards the singularity at the center, where densities become infinite and our current understanding of physics can no longer apply. Here, space and time could essentially swap roles, making the singularity a destination in time rather than in space. This region remains one of the most enigmatic in all of cosmology, highlighting the limits of our current understanding and the incredible challenges that lie ahead in unlocking the secrets of black holes. The black hole information paradox is a perplexing problem standing at the intersection of quantum mechanics and general relativity. It arises from Stephen Hawking's discovery that black holes are not entirely black but emit tiny amounts of radiation known as Hawking radiation. This radiation suggests that black holes can eventually evaporate completely. If they do, what happens to the information that fell into the black hole? This question is at the heart of the paradox because, according to quantum mechanics, information cannot be destroyed. One proposed resolution involves the idea that information might be somehow encoded in the Hawking radiation itself, albeit in an extremely scrambled form. This concept is often likened to burning a book. The information is still present in the smoke and ash, though it is essentially unreadable. Some theoretical physicists argue that black holes could similarly release information through subtle correlations in the emitted radiation. However, accurately describing this process remains a formidable challenge. Another fascinating perspective comes from the holographic principle, which posits that all the information about the three-dimensional interior of a black hole might be encoded on its two-dimensional surface, the event horizon. This idea suggests that the universe itself could be a hologram, where everything we perceive in 3 dimensions is a projection of information stored on a two-dimensional boundary. The implications of this principle are vast, stretching far beyond black holes to potential insights into the very nature of reality. Recent advancements in the field of quantum gravity, particularly through string theory and loop quantum gravity, also offer potential pathways to resolving the paradox. These theories aim to reconcile the macroscopic world of general relativity with the microscopic realm of quantum mechanics. Some promising models propose that black holes could retain a quantum footprint even after they evaporate, preserving information in a fundamentally new way. While no definitive answer has emerged yet, these theoretical efforts continue to push the boundaries of our understanding. The black hole information paradox remains one of the most exciting areas of research in physics, driving scientists to question and refine some of the most fundamental principles governing our universe. Closed time-like curves, often abbreviated as CTCs, are theoretical paths in space-time that loop back on themselves, effectively allowing for a kind of time travel. If CTCs exist in the universe, it would mean that an object or even information could travel backwards in time, potentially returning to its own past. This concept emerges from Einstein's general relativity, where space-time can be curved or warped by mass and energy, creating these exotic loops. The existence of CTCs could lead to some mind-bending possibilities and significant philosophical and physical implications. One of the most famous consequences is the possibility of paradoxes, such as the so-called grandfather paradox, where a time traveler could theoretically prevent their own existence by altering past events. If someone traveled back and prevented their ancestors from meeting, it would create a logical inconsistency since the time traveler would never have been born to go back in the first place. To resolve these paradoxes, several theoretical solutions have been proposed. One is the Novikov self-consistency principle, which posits that any actions taken by a time traveler were always part of history, ensuring that paradoxical situations cannot arise. In other words, any event that could lead to a paradox would have a probability of 0. This principle suggests that the universe's history is self-consistent and unchangeable despite the presence of time travel. Another interesting proposition is the concept of multiple timelines, or the many worlds interpretation. This idea suggests that any action taken by a time traveler could create a new parallel timeline, leaving the original timeline unchanged. In this framework, each decision or action creates a branching universe where all possible outcomes exist concurrently, and paradoxes are avoided because each branch follows its own consistent history. While CTCs remain theoretical, their potential existence stimulates profound discussions on the nature of time, causality, and the fundamental architecture of our universe. The study of CTCs and time travel continues to push the boundaries of physics and philosophy, encouraging us to rethink our understanding of time and reality. Whether these exotic phenomena exist or not, they inspire deeper inquiry into the mysteries of space-time. Quantum entanglement challenges our understanding of causality in space by presenting a phenomenon where two or more particles become linked in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance separating them. Albert Einstein famously described this as spooky action at a distance, because it seems to contravene the classical theory of relativity, which dictates that information cannot travel faster than the speed of light. In classical physics, causality implies a cause and effect relationship that is limited by the speed of light. However, in the quantum realm, entangled particles clear these barriers, suggesting a form of non-locality where spatial distance becomes irrelevant. Measuring the state of one entangled particle instantaneously affects the state of its partner, no matter how far apart they are. This instantaneous influence implies that information transfer between entangled particles is somehow occurring at a speed faster than light, presenting a conundrum that defies our conventional understanding of causality. The key to resolving this paradox lies in the nature of quantum information itself. While entangled particles exhibit correlations that seem to instantaneously communicate over vast distances, these correlations do not transmit usable information in the classical sense. This means you cannot send a signal or message using quantum entanglement alone, thereby preserving the no faster than light information rule dictated by relativity. However, the mystery remains in how these correlations form and maintain themselves instantaneously over any distance. Efforts to reconcile these seemingly incompatible aspects of quantum mechanics and relativity continue to be a major focus of modern physics. One potential avenue includes the development of quantum field theory, which aims to describe all fundamental forces and particles within a single framework. Another promising path is the study of quantum gravity, which seeks to unite quantum mechanics and general relativity into a coherent theory that can fully explain entanglement and its implications for space, time, and causality. In sum, quantum entanglement challenges our classical notions of space and causality, introducing a reality where particles can exhibit instantaneous correlations regardless of distance. While this does not allow for faster-than-light communication, it nudges us closer toward understanding the deeply intertwined fabric of the universe, hinting at profound insights that lie just beyond our current grasp. The arrow of time, a term coined by physicist Arthur Eddington, describes the one-way direction or asymmetry of time. It's the concept that time seems to move only forward, from the past to the future, and never in reverse. This arrow of time is deeply connected to entropy, a fundamental concept in thermodynamics. Entropy is a measure of the level of disorder or randomness in a system. According to the second law of thermodynamics, in an isolated system, the total entropy can never decrease over time. It either increases or remains constant. This law implies that natural processes tend to move from order to disorder. For example, a cup of hot coffee, when left alone, will cool down rather than heat up, because the combined system of the coffee and its surroundings increases in entropy. This increase in entropy is what gives us a perceived arrow of time. As time progresses, the universe moves from a state of lower entropy to higher entropy. The concept of entropy provides a thermodynamic explanation for the arrow of time, but other aspects of physics offer additional insight. In cosmology, the direction of time is linked to the Big Bang. The universe began in a highly ordered, low-entropy state. As it has expanded, entropy has increased, giving a temporal direction to the unfolding events within the cosmos. This cosmic evolution underscores why we observe time moving forward, aligned with the ever-expanding and cooling universe. From a microscopic standpoint, the laws of physics are fundamentally time-symmetric. Equations governing the motion of particles work equally well whether time moves forward or backward. However, once we aggregate large numbers of particles, the statistical nature of entropy takes over, enforcing a macroscopic arrow of time. The momentary configurations of particles in a particular time direction lead to higher probabilities of increased disorder, reinforcing the forward march of time. The psychological perception of time also plays a role. Human consciousness experiences the accumulation of memories in one direction, from past to future, which contributes to our intuitive understanding of time's arrow. Our brains encode experiences sequentially, which further solidifies our lived experience of forward-moving time. The true nature of the arrow of time is therefore multifaceted, influenced predominantly by the second law of thermodynamics, cosmological evolution, and human perception. Despite the time-symmetric nature of fundamental physics equations, the larger structure of the universe and the behavior of entropy give us this inevitable sense of time always moving forward. The apparent causal nature of quantum mechanics arises from the peculiar and non-intuitive behavior of particles at the smallest scales, challenging our classical understanding of cause and effect. Unlike classical physics, where the behavior of objects is predictable and deterministic, quantum mechanics operates on a foundation of probabilities and uncertainties. A fundamental principle in quantum mechanics is the wave-particle duality, where entities such as electrons can exhibit both particle-like and wave-like properties. This principle is governed by the Schrödinger equation, predicting the probability distribution of a particle's position and momentum. Rather than pinpointing exact outcomes, Quantum mechanics provides a range of potential outcomes, each with a specific likelihood. The concept of superposition further exacerbates the acausality issue. In a superposition state, a quantum particle can exist in multiple states simultaneously, like being in two places at once. It's only upon measurement that the particle collapses into a single state. This collapse seems acausal because there's no clear deterministic process explaining why the particle chooses a specific state over another. Entanglement, as previously discussed, compounds the mystery. When particles become entangled, the state of one particle instantaneously affects the state of the other, regardless of distance. This instantaneous correlation appears acausal because it defies classical causal chains, where an effect should not precede or instantaneously follow its cause across space-time. Physicists use mathematical frameworks, like the probabilistic wave function, to describe these phenomena, yet the underlying mechanisms remain opaque. Theoretical interpretations, such as the Copenhagen interpretation, assert that quantum mechanics doesn't describe objective reality, but only our knowledge of it. The many worlds interpretation suggests that every possible outcome actually occurs in a separate, parallel universe, effectively sidestepping the need for causal explanations within any single timeline. While these interpretations provide frameworks to understand quantum phenomena, they highlight the distinction between classical and quantum causality. In the classical world, events are linked by clear causal chains governed by deterministic laws. Quantum mechanics, however, suggests that these familiar chains unravel at microscopic scales, replaced by a probabilistic framework that resists causal description. Thus, the apparent acausality in quantum mechanics challenges our conventional notions of cause and effect, pointing to a deeply probabilistic and interconnected nature of reality. Ongoing research continues to probe these mysteries, seeking to reconcile our macroscopic causal understanding with the enigmatic behavior observed in the quantum realm. If tachyons, hypothetical particles that travel faster than the speed of light, were proven to exist, the implications for our understanding of physics and the nature of the universe would be profound. According to Einstein's theory of relativity, nothing with mass can surpass the speed of light. Tachyons, by their very definition, would defy this cornerstone of modern physics. To begin with, the existence of tachyons would introduce the possibility of communication and travel at superluminal speeds. This could challenge the very structure of causality, the principle that cause precedes effect. If information or matter could travel faster than light, it might allow for effects to be observed before their causes, potentially enabling scenarios like sending information back in time. This would open up a host of paradoxes and necessitate a fundamental rethinking of the causal structure of the universe. Moreover, tachyons would revolutionize our understanding of energy and momentum. In relativity, as an object approaches the speed of light, its relativistic mass increases, requiring infinite energy to reach the speed of light itself. Tachyons, however, theoretically possess an imaginary mass and would require infinite energy to slow down to the speed of light, behaving in an inverted manner compared to normal particles. This would necessitate new physics models to explain their behavior and interactions with other particles. Another implication involves quantum field theory. If tachyons exist, they might potentially influence quantum fields in ways that could lead to new forms of radiation or interactions. Their existence might demand new types of field theories or modifications to existing ones to consistently incorporate faster-than-light particles without leading to inconsistencies or infinities in the equations. Finally, the discovery of tachyons might revolutionize technology in unpredictable ways. Just as the discovery of the electron led to the development of electronics and modern technology, uncovering the characteristics and potential control of tachyons could lead to unforeseen advancements. Superluminal communication, for instance, if harnessed, could radically change how we share information across vast distances, reshaping our approach to space exploration and beyond. The hypothetical existence of tachyons would necessitate a significant overhaul of current physical theories. challenge the classical notion of causality, and potentially pave the way for groundbreaking technological advancements. The scientific community remains cautious, as the implications are not just theoretical curiosities, but could fundamentally alter our understanding of the universe. Time dilation, a fascinating consequence of Einstein's theory of relativity, profoundly affects our observations of distant cosmic events, revealing the intricate relationship between time, space, and gravity. This phenomenon can occur in two main contexts: gravitational time dilation and velocity-based time dilation. Gravitational time dilation arises from the presence of strong gravitational fields. According to general relativity, time passes more slowly near massive objects compared to regions with weaker gravitational fields. For instance, time for an observer near a massive star or black hole would tick more slowly relative to someone far away from these objects. When we observe light from regions close to black holes, the photons experience this time dilation, appearing redshifted due to the slower passage of time near the massive object. This redshift can give us clues about the intensity of the gravitational field and the nature of space-time around these massive cosmic bodies. Velocity-based time dilation, explained by special relativity, occurs when objects move at speeds close to the speed of light. Time for these rapidly moving objects slows down relative to stationary observers. When we observe distant galaxies moving away from us due to the expansion of the universe, particularly those at speeds near light, we witness this time dilation effect. Supernovae in these distant galaxies, for example, appear to evolve more slowly than those in nearby galaxies. This stretched-out timeline provides astronomers with a unique way to study the properties and evolution of these explosive events over extended periods. In the broader cosmic context, the expansion of the universe itself introduces time dilation effects. As we look at increasingly distant objects, we are also looking back in time, observing them as they were billions of years ago. Due to the universe's expansion, the light from these distant sources is redshifted, and the emitted wavelengths are stretched, slowing down the observed progression of events. These time dilation effects offer invaluable tools for astronomers and physicists. By analyzing how light and events are altered by time dilation, scientists can extract detailed information about the motion, distance, and gravitational influences of cosmic objects. This understanding helps to refine models of cosmic evolution, the life cycles of stars, and the workings of black holes. Time dilation not only challenges our perception of time, but also enriches our comprehension of the universe's dynamic and interconnected nature. The nature of time before the Big Bang is a deeply philosophical and complex question that pushes the boundaries of our current understanding of physics and cosmology. Traditional notions of time and space break down as we approach the initial singularity, where density and temperature become infinite, according to classical general relativity. This singularity poses significant challenges, as the laws of physics as we know them cease to function in their conventional forms. One influential perspective is offered by quantum cosmology, which seeks to integrate principles of quantum mechanics with general relativity to understand the early universe. In this framework, time near the Big Bang might not resemble the linear, continuous dimension we experience. Some theories, like those proposed by Stephen Hawking and James Hartle, suggest the idea of imaginary time. They propose that what we perceive as time could transform into a spatial dimension near the Big Bang, effectively removing the singular beginning and creating a finite but unbounded universe. In this model, asking what happened before the Big Bang would be analogous to asking what lies north of the North Pole, a question rendered meaningless by the geometry of Earth's surface. Another compelling idea comes from string theory and the concept of the multiverse. In some interpretations, our universe could be one of many within a vast multiverse. Here, the Big Bang might have been a localized event in a far more extensive, possibly eternal framework. If this is the case, what we perceive as the beginning of time could be a phase transition in a pre-existing higher dimensional timeline. This scenario allows for the possibility that time and space existed in some form before the Big Bang, suggesting a cyclical or bouncing universe where Big Bangs occur repeatedly. Loop quantum gravity, another approach to merging quantum mechanics with general relativity, proposes yet another perspective. This theory suggests that the singularity at the Big Bang might be resolved into a transition between different phases of the universe, where time continues through these phases without the singular breakdown predicted by classical theories. In such a framework, the Big Bang could be a bounce from a previous contracting phase, implying time existed in forms antecedent to our current expanding universe. While these theories remain speculative and require empirical validation, they illustrate the diverse approaches scientists are taking to tackle the enigma of time's origin. As our understanding of quantum mechanics, cosmology, and theoretical physics progresses, we may come closer to unraveling this paradox. The nature of time before the Big Bang may ultimately reveal new aspects of reality, transforming our comprehension of existence itself. Different models of the multiverse offer varying perspectives on the concept of time, reflecting the diversity of theoretical frameworks attempting to describe a reality beyond our observable universe. Here are several key models and their approaches to the nature of time. In the bubble universe or eternal inflation model, time is treated as an ever-expanding entity. According to this theory, our universe is just one bubble within a vast multiverse where inflation, an exponential expansion of space, continuously spawns new bubble universes. Each bubble universe may have its own distinct laws of physics and timelines. Within each bubble, time progresses as we experience it, but across different bubbles, the concept of time becomes less straightforward. Time could be regarded as branching endlessly, with each new universe experiencing its own separate timeline. String theory's landscape. Multiverse envisions a multitude of universes arising from different possible configurations of fundamental strings or branes. In this model, each universe corresponds to a different solution to the string equations, leading to a landscape of possible universes with varying physical laws and constants. Time in each universe behaves according to its internal physical laws. In some scenarios, time could be similar to our own, while in others it might follow entirely different structures. This multiplicity complicates a unified sense of time across universes, suggesting that each bubble or pocket universe has its own independent timeline. The many worlds interpretation of quantum mechanics provides another intriguing perspective. In this interpretation, every quantum event spawns a branching of instantaneous parallel universes, each representing a different outcome of the event. Time, within each branch, moves forward independently, but the branching process creates a complex, tree-like structure of timelines. Here, time is a constantly diverging entity, with every quantum decision splitting the timeline into new, parallel realities. Loop quantum gravity and spin foam models propose yet another view, building on the idea of quantized spacetime. In these models, time is not continuous but exists in discrete chunks or quantum units. The multiverse concept in this framework might involve interconnected spin foams representing different regions or phases of the universe, each with its own localized, quantized timeline. The connection between these regions could imply that time behaves differently in each domain, possibly offering a more fragmented and discrete approach to the nature of time. The cyclic or ekpyrotic universe. Models adds the notion of a repeating, oscillating cosmos to the multiverse dialogue. In these models, universes undergo endless cycles of expansion and contraction, akin to the Hindu concept of cosmic cycles. Time in this scenario extends infinitely, but in a cyclical fashion, where each Big Bang and subsequent collapse resets the cosmic clock. Thus, time is both linear within each cycle, but also cyclical on a grander scale, perpetually renewing itself. These various models reflect the ongoing struggle to comprehend the true nature of time within the broader context of a multiverse. Whether time is viewed as branching, cycling, discrete, or varying across different domains, these theories collectively expand our conceptual boundaries, challenging us to envision a reality far more intricate and diverse than our singular universe suggests. As we refine our theoretical tools and gather new data, our understanding of time in the potential multiverse will likely evolve, offering ever richer insights into the fabric of existence. Quantum vacuum fluctuations are one of the most intriguing phenomena in quantum field theory, shedding light on the dynamic nature of what we often consider empty space. Even the seemingly desolate intergalactic space is teeming with transient, fluctuating energy, challenging our classical notion of a true vacuum. According to quantum mechanics, a vacuum is not a simple void, but a seething, restless environment constantly abuzz with virtual particles popping in and out of existence. These particles, which include pairs of particles and antiparticles, emerge spontaneously due to the uncertainty principle. This principle states that it is fundamentally impossible to precisely measure both the energy and the time duration of these particles simultaneously. As a result, these virtual particles appear briefly before annihilating each other almost immediately. In intergalactic space, far from gravitational influences and astronomical bodies, these vacuum fluctuations play a subtle yet crucial role. They contribute to what is known as vacuum energy, which has a profound influence on the structure and dynamics of the universe. One of the most significant implications of this vacuum energy is its contribution to dark energy, the mysterious force driving the accelerated expansion of the universe. While dark energy's exact nature remains elusive, it is thought to be linked to the energy density of the vacuum itself. Additionally, quantum vacuum fluctuations have practical consequences observable through phenomena like the Casimir effect. In this effect, two closely placed uncharged metallic plates in a vacuum experience an attractive force due to the alteration of vacuum fluctuations between them. While such an experiment is more challenging in the vastness of space, it underscores the tangible presence of quantum fluctuations even in the emptiest regions of the cosmos. These fluctuations might also influence cosmic microwave background radiation and large-scale structures, as initial quantum fluctuations in the early universe are believed to have grown into the vast cosmic web of galaxies and clusters we observe today. Small density variations in this primordial quantum sea were amplified by cosmic inflation, eventually leading to the large-scale structure of the universe. Quantum vacuum fluctuations in intergalactic space reveal that even the emptiest pockets of the cosmos are far from empty. They are filled with energetic activity governed by the laws of quantum mechanics, contributing to the fundamental forces and large-scale behaviors of the universe. This ever-present energy challenges our perceptions and invites further exploration into the profound mysteries of the quantum realm and its impact on cosmic scales. Quantum tunneling plays a crucial role in processes occurring within stellar cores, enabling nuclear reactions that would otherwise be impossible under the given conditions. This fascinating quantum phenomenon allows particles to pass through energy barriers that, according to classical physics, they shouldn't be able to surmount due to insufficient energy. In the intense environment of a star's core, where temperatures and pressures are extraordinarily high, atomic nuclei are in constant motion and frequently collide. For nuclear fusion to occur, these nuclei must overcome the strong electrostatic repulsion between positively charged protons. Classically, fusion would require temperatures so high that stars like our Sun would be unable to sustain nuclear reactions. However, thanks to quantum tunneling, these reactions can occur at the comparatively lower temperatures present in stars. When protons collide within a stellar core, quantum tunneling allows them to penetrate the Coulomb barrier, the energy barrier due to electrostatic repulsion. Even at lower energies, there's a finite probability that the protons can tunnel through this barrier and come close enough for the strong nuclear force to take over, facilitating fusion. In the case of the Sun, for example, quantum tunneling enables the proton-proton chain reaction, where hydrogen nuclei fuse to form helium, releasing vast amounts of energy in the process. This quantum tunneling is not limited to hydrogen fusion. It is also essential in more massive stars where different nuclear fusion processes occur. For instance, during the later stages of stellar evolution, heavier elements fuse in advanced nuclear burning stages, such as the carbon-nitrogen-oxygen cycle or the triple alpha process, which produces carbon from helium. In these processes, quantum tunneling similarly allows nuclei to overcome their mutual repulsion and fuse, creating heavier elements and releasing energy that supports the star against gravitational collapse. This tunneling effect is so fundamental that it's one of the pivotal mechanisms explaining why stars shine and how they synthesize new elements. Without quantum tunneling, the rates of fusion reactions in stellar cores would be prohibitively slow, and stars would be unable to sustain the processes that lead to their lifetimes and eventual evolution. The energy produced through these reactions is what powers stars, providing the heat and light that are essential for the existence of life as we know it. Quantum tunneling is a key enabler of the nuclear reactions driving stellar cores. By allowing particles to pass through energy barriers, it permits fusion at temperatures and densities achievable within stars, ultimately influencing the life cycles of stars and the nucleosynthesis of elements that build the universe. Quantum entanglement, one of the most intriguing and non-intuitive phenomena in quantum mechanics, might play a significant role in various stages of the universe's evolution, hinting at profound connections between microscopic quantum processes and macroscopic cosmic structures. In the early universe, just after the Big Bang, quantum fluctuations played a critical role in shaping the large-scale structure we observe today. During the period of cosmic inflation, the rapid expansion magnified these minute quantum fluctuations to macroscopic scales. These tiny perturbations eventually led to the formation of the cosmic web of galaxies, clusters, and voids. Quantum entanglement could have been crucial in these early fluctuations, potentially creating correlations over vast distances which would impact the distribution and properties of matter and energy throughout the cosmos. Entanglement also ties into the realm of black hole physics and the information paradox. When matter falls into a black hole, the information about the quantum states of particles appears to be lost, leading to a paradox in the context of quantum mechanics, which stipulates that information cannot be destroyed. Entangled particles near the event horizon might play a role in understanding these processes, potentially linking the interior and exterior states of the black hole. Theoretical approaches like the holographic principle suggest that the information is encoded on the event horizon, maintaining the integrity of quantum information and hinting at a deep and still understood connection between gravity and quantum mechanics. Additionally, quantum entanglement might influence the nature of dark energy and the accelerated expansion of the universe. Some hypotheses suggest that entangled states could be a source of dark energy, contributing to the vacuum energy that drives cosmic acceleration. While this idea remains speculative, it points toward the potential influence of quantum phenomena on a cosmological scale, suggesting enmeshed relationships between quantum mechanics and the universe's macroscopic expansion. On a more speculative front, the foundational role of entanglement in forming the universe raises questions about the very fabric of spacetime. Some approaches in quantum gravity suggest spacetime itself could emerge from entanglement, weaving a quantum fabric where the geometry of space and time arises from complex networks of entangled particles. This perspective posits that understanding entanglement could eventually lead to a deeper theory that unifies gravity with quantum mechanics, a long-sought goal in theoretical physics. Quantum entanglement might have played pivotal roles throughout the universe's history, from the initial conditions set by quantum fluctuations to the potential solutions to the black hole information paradox, the nature of dark energy, and the fundamental structure of space-time itself. These potential roles underscore the profound and intricate ways in which quantum mechanics connects to the universe's grand cosmic narrative, suggesting pathways for future exploration and deeper understanding of the cosmos. Quantum effects significantly influence the behavior of matter in neutron stars, which are among the densest objects in the universe. These effects dictate the exotic properties and behaviors observed within these stellar remnants, especially given their extreme conditions of immense pressure and density. One of the primary quantum effects at play is the Pauli exclusion principle, which states that two fermions, particles like neutrons, protons, and electrons that follow Fermi-Dirac statistics, cannot occupy the same quantum state simultaneously. In the core of a neutron star, this principle is crucial because it prevents the neutrons from being compressed into an even denser state. Even at such extreme densities, the exclusion principle creates a powerful quantum pressure known as degeneracy pressure. This pressure helps counteract the immense gravitational forces that would otherwise cause the star to collapse further, such as into a black hole. Additionally, closely related to the Pauli exclusion principle is neutron degeneracy pressure, which supports neutron stars against further gravitational collapse. This degeneracy pressure arises due to the cramped conditions of neutrons in such a dense environment. The quantum mechanical concept of degeneracy pressure explains why neutron stars, despite their incredibly high densities, can remain stable. Another critical quantum effect involves superfluidity. In a neutron star's core, neutrons can form Cooper pairs and behave as a superfluid. This means they flow without viscosity, enabling the star's interior to exhibit unique properties. Superfluidity in neutron stars influences how angular momentum is transferred within the star, especially during phenomena like glitches, where the rotational speed of the star suddenly changes. These glitches are thought to result from interactions between the star's crust and its superfluid core. The presence of extremely strong magnetic fields in neutron stars, particularly in magnetars, can also result in curious quantum effects. Quantum electrodynamics predicts that in the presence of immensely strong magnetic fields, the vacuum itself can become polarized, a phenomenon known as vacuum birefringence. This effect could influence the propagation of light near the star, providing insights into the star's magnetic field strength and structure through its effects on photon behavior. Moreover, neutron stars harbor significant densities, such that particles' energies can reach the scales where quantum chromodynamics, the theory describing strong interactions, becomes critical. It is at these densities that novel states of matter, such as quark-gluon plasma, or even possible exotic phases like color superconductivity, might exist. In these phases, quarks, the building blocks of neutrons and protons, could exist in free or nearly free states, vastly different from the regular quark confinement found within atomic nuclei. Quantum effects are integral to understanding the behavior of matter in neutron stars. From degeneracy pressures to superfluidity and quantum electrodynamics effects to potential exotic states of matter, these quantum phenomena govern the stability, structure, and dynamism of one of the universe's most extraordinary objects. The study of neutron stars provides a unique astrophysical laboratory to explore and test the extremes of quantum theory and transformative states of matter. Quantum decoherence plays a pivotal role in bridging the gap between the strange world of quantum mechanics and the classical world we observe in our everyday lives. In simple terms, decoherence describes the process by which a quantum system loses its quantum behavior, such as superposition and entanglement, as it interacts with its environment. This loss of coherence transforms the system's behavior into classical states that we can measure and see. In the context of cosmology, decoherence is essential for understanding the transitional behavior of the early universe. During the period after the Big Bang, the universe was in a highly energetic and quantum state. As the universe expanded and cooled, quantum fluctuations and superpositions transitioned into classical fluctuations. This essentially seeded the structure of the cosmos, laying down the groundwork for the formation of galaxies, stars, and planets. Observation of the cosmic microwave background radiation, the leftover thermal imprint from the Big Bang, provides a window into this transition. The tiny temperature fluctuations within this radiation reflect the primordial quantum perturbations that decohered into classical density variations. These density variations eventually led to the large-scale structures we observe in the universe today. Moreover, decoherence helps us understand why macroscopic bodies like planets and stars do not exhibit quantum behavior, despite being made up entirely of quantum particles. It's the same principle that allows us to see quantum mechanics evidence only in controlled laboratory conditions, where interactions with the environment can be minimized. Therefore, quantum decoherence is not just a fascinating quantum phenomenon, but a crucial ingredient in the tapestry of cosmological evolution. Quantum gravity aims to merge the principles of quantum mechanics with general relativity to describe the universe's fundamental fabric at the smallest scales. Singularities in black holes, where densities and curvatures become infinite and the known laws of physics break down, are one of the most pressing problems this theory seeks to resolve. Traditional general relativity predicts that the core of a black hole, known as the singularity, contains a point where gravitational forces are infinitely strong. This results in the breakdown of physical laws as we know them. Quantum gravity, however, introduces the concept that space-time at these extreme conditions may no longer be smooth and continuous, but rather quantized or composed of discrete units. One key idea emerging from quantum gravity theories, such as loop quantum gravity, suggests that space-time is woven from tiny loops of quantum fields rather than being a continuous fabric. These loops could prevent the gravitational collapse from squeezing matter into an infinitely small point. Instead of a singularity, the core would attain a very high but finite density, fundamentally altering our understanding of black hole interiors. Additionally, in another prominent approach known as string theory, the fundamental particles are considered as one-dimensional strings rather than point-like entities. This perspective adds extra dimensions and could diffuse the intense gravitational forces that create singularities. By spreading out these forces over these additional dimensions, the singularity might effectively be smoothed out, avoiding the infinite values predicted by general relativity. Exploring these quantum gravity solutions could not only address the enigmatic singularities within black holes, but also provide profound insights into the early universe's nature, where similar extreme conditions likely existed. This unification promises to illuminate new realms of physics, fundamentally reshaping our comprehension of the cosmos. Virtual particles are intriguing phenomena predicted by quantum field theory, suggesting that they constantly pop in and out of existence in the vacuum of space. Near black holes, especially close to their event horizons, these ephemeral particles exhibit fascinating behaviors that are critical to understanding various extreme physical processes. The event horizon, the boundary beyond which nothing, not even light, can escape a black hole's gravitational pull, creates a unique environment for these virtual particles. Due to the intense gravitational energy near the event horizon, virtual particles can gain enough energy to become real particles. This process is known as Hawking radiation, named after the physicist Stephen Hawking, who proposed it. Hawking radiation occurs when a pair of virtual particles form near the event horizon. Usually these pairs annihilate each other quickly. However, the powerful gravitational field of a black hole can separate them. One particle may fall into the black hole, while the other escapes into space as real radiation. This radiation leads to the gradual loss of mass and energy from the black hole, implying that black holes can slowly evaporate over immense timescales. The extreme conditions near black holes not only amplify the behaviors of virtual particles, but also provide a natural laboratory to test theories of quantum gravity and thermodynamics. The interactions between virtual particles and black holes challenge our current understanding of information conservation and entropy, highlighting unresolved puzzles in physics. For instance, the information paradox questions whether information swallowed by a black hole is truly lost forever or somehow encoded within the Hawking radiation. Understanding the nature and behavior of virtual particles near black holes not only enriches our grasp of quantum field theory, but also pushes the boundaries of how we comprehend gravity, thermodynamics, and the very fabric of reality. Such extreme environments serve as crucibles for our most advanced theories, compelling us to refine and rethink our models of the universe. Quantum effects play a surprisingly fundamental role in the story of galaxy formation. Shortly after the Big Bang, during the universe's infancy, quantum fluctuations stirred within the nascent cosmic soup. These minute perturbations in the energy density eventually seeded the large-scale structures we observe in the cosmos today. As the universe rapidly expanded in a phase known as cosmic inflation, these tiny quantum fluctuations stretched to macroscopic scales. Inflation magnified these subatomic irregularities into slight variations in the density of the primordial plasma. These variations are imprinted in the cosmic microwave background radiation, which is the afterglow of the Big Bang, observable as tiny temperature fluctuations spread across the sky. Over the eons, these initial quantum perturbations acted as blueprints for the formation of cosmic structures. Regions with slight overdensities began to gravitationally attract more matter, gradually growing into the massive concentrations of gas and dark matter that would later coalesce into galaxies. Meanwhile, less dense regions correspondingly evolved into vast cosmic voids. Dark matter, composed of yet unidentified particles that do not emit or absorb light, significantly amplifies the influence of these quantum-originated density fluctuations. It clumped together first, creating gravitational wells that ordinary matter eventually fell into, leading to the formation of galaxies, stars, and planets. Without the initial nudge from quantum fluctuations, the cosmos might have remained an almost featureless expanse devoid of the complex structures we see today. Thus, quantum effects in the universe's formative moments provided the essential seeds for galaxy formation. By bridging the micro and macro scales, these quantum perturbations remind us how intricately connected the smallest components of our universe are to its grandest structures, linking the ethereal nature of quantum mechanics with the majestic beauty of galaxies. Quantum fluctuations are pivotal in the generation of cosmic magnetic fields, serving as initial disturbances that can evolve into magnetic structures permeating the universe. These fluctuations, remnants from the earliest moments post-Big Bang, provided primordial seeds that influenced various processes, one of which is the generation of cosmic magnetic fields. During the early universe, inflation stretched these quantum fluctuations to astronomical scales. This rapid expansion resulted in tiny irregularities in the energy density of the universe. These irregularities are imprinted in the cosmic microwave background that scientists study to understand the early universe's conditions. Quantum fluctuations, therefore, acted as the foundational disturbances in the otherwise uniform field of early cosmic plasma. As the universe transitioned from this dense, hot plasma state to form atoms and galaxies, these initial disturbances contributed to turbulence and plasma movements. These movements created the dynamo effect, a process where the kinetic energy of conducting fluids, such as plasma, converts into magnetic field energy. The primordial perturbations led to the motion and flow of charged particles, generating seed magnetic fields. Over time, these seed fields were amplified through various astrophysical processes, including the collapse of gas clouds, supernova explosions, and the churning motions of galaxies. These processes acted like cosmic dynamos, continuously regenerating and enhancing the magnetic fields. Today, these fields stretch across galaxies, star systems, and the interstellar medium, playing critical roles in star formation, cosmic ray propagation, and even galaxy dynamics. Thus, quantum fluctuations did not just shape the large-scale structure of the universe, but also laid the groundwork for cosmic magnetic fields. This intricate dance between the quantum microcosm and the vast magnetic tapestries woven across the cosmos showcases the profound interconnectedness of fundamental physics. Quantum uncertainty, encapsulated by Heisenberg's uncertainty principle, profoundly impacts our understanding of the universe's initial conditions by dictating that certain pairs of physical properties cannot be precisely known simultaneously. For instance, you cannot precisely determine both the position and momentum of a particle at the same time. This intrinsic uncertainty plays a crucial role in the universe's earliest moments, especially during the period of cosmic inflation. In the vacuum of space, quantum uncertainty causes fluctuations even when it seems entirely empty. These fluctuations are fleeting changes in energy that result in the creation and annihilation of particle pairs. During cosmic inflation, the rapid expansion of space stretched these quantum fluctuations to macroscopic scales, embedding subtle differences in density and temperature across the universe. These primordial perturbations set the stage for the large-scale structures we observe today. The imprint of these early quantum fluctuations is visible in the cosmic microwave background radiation, the ancient afterglow of the Big Bang. The tiny variations in this radiation's intensity map out the initial conditions of the universe. Areas slightly denser than their surroundings began to attract more matter due to gravity, eventually forming galaxies, stars, and clusters. Without quantum uncertainty, these initial conditions would not have varied, and the cosmos might have remained a uniform, featureless expanse. Additionally, quantum uncertainty challenges the deterministic view of classical physics, where the universe's initial conditions would precisely determine its entire future. Instead, it introduces a probabilistic nature to the universe's evolution, allowing for a spectrum of possibilities. This probabilistic nature is crucial in understanding events like particle interactions, energy distributions, and even the formation of fundamental forces in the early universe. Therefore, quantum uncertainty not only provides a framework to interpret the origins and evolution of cosmic structures, but also underscores the inherent unpredictability woven into the fabric of reality. This interplay of certainty and randomness invites us to contemplate the profound complexity of the universe from its very inception. Cosmic phase transitions in the early universe are thought to have been driven by changes in the state of matter and energy as the universe evolved and cooled from its extraordinarily hot and dense beginnings. These transitions are akin to the way water changes from steam to liquid to ice, but on a cosmic scale involving fundamental forces and particles. In the moments following the Big Bang, the universe underwent several critical phase transitions. One of the earliest and most significant of these is believed to be the separation of the fundamental forces. In the intensely hot conditions of the early universe, it is postulated that the four known fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were unified into a single superforce. As the universe expanded and cooled, these forces began to decouple from each other in a series of phase transitions. For instance, the strong force, which holds atomic nuclei together, likely separated from the electroweak force within the first fractions of a second after the Big Bang. Another crucial phase transition occurred during a period known as cosmic inflation. During this brief but dramatic expansion, the universe grew exponentially faster than the speed of light. The inflaton field, a hypothetical scalar field, is thought to have driven this rapid growth. As the inflationary period ended, the energy stored in this field transitioned into particles and radiation, filling the universe with the conditions necessary for the formation of matter as we know it. Later, as the universe continued to cool, another significant phase transition known as quark confinement occurred. During this transition, free quarks, elementary particles and fundamental constituents of matter, became bound together by the strong force to form protons, neutrons, and other hadrons. This transition marked the end of the quark-gluon plasma state that dominated the universe's earliest moments. These phase transitions were fundamental to shaping the universe's evolution, leading to the universe filled with the complex structures we observe today. By understanding these transitions, scientists can piece together the critical events that forge the cosmic landscape from a hot soup of particles to the intricately structured cosmos. The apparent fine-tuning of universal constants is one of the most intriguing puzzles in cosmology and physics. Universal constants, such as the gravitational constant, the fine structure constant, and the values of fundamental particle masses, appear to be finely tuned to such precise values that even a slight alteration to them could render the universe inhospitable to life as we know it. One leading explanation for this fine-tuning is the anthropic principle, which suggests that the constants of the universe must fall within a very narrow range that allows for the existence of observers like us. Essentially, if the universe were not fine-tuned, we would not be here to ponder about it. This viewpoint makes the existence of our universe an observed necessity simply because we are here to observe it. Another compelling explanation comes from the multiverse theory. This hypothesis posits that our universe is but one of many universes, each with its own set of physical constants and laws of physics. In this vast multiverse, some universes may have constants that do not support life, and others might. Ours just happens to be one where the constants align perfectly to permit galaxies, stars, planets, and ultimately, life. Additionally, some scientists explore the possibility that what we perceive as fine-tuning might be a natural outcome of deeper, underlying principles in fundamental physics. These yet-to-be-discovered principles might dictate that the constants take the values they do inevitably. String theory and other advanced theoretical frameworks offer potential mechanisms through which these constants are determined, suggesting they are not randomly assigned, but arise naturally from the fabric of the universe's fundamental laws. The fine-tuning of universal constants remains an open question, but these various theories collectively frame our understanding. Whether it is through the anthropic principle, the existence of a multiverse, or undiscovered laws of nature, the seemingly improbable alignment of the constants continues to inspire and challenge our grasp of the cosmos. Cosmic inflation is a theory proposed to explain several perplexing observations about the early universe. It posits that a fraction of a second after the Big Bang, the universe underwent an extremely rapid and exponential expansion. This period of inflation smoothed out any initial irregularities and set the stage for the structured universe we see today. The nature of cosmic inflation is rooted in the concept of an inflaton field, a hypothetical scalar field that pervaded the early universe. This field had a high energy density, causing space to expand exponentially. Physicist Alan Guth first proposed this idea in the early 1980s to address various cosmological problems, such as the horizon problem and the flatness problem. The horizon problem concerns the uniformity of the cosmic microwave background radiation. Distant regions of the universe are remarkably uniform in temperature, even though they are so far apart that they should not have been in causal contact under standard Big Bang cosmology. Inflation solves this by stretching a tiny uniform region to enormous size, ensuring large-scale uniformity. The flatness problem relates to the universe's geometry. Inflation drove the universe to become very flat, aligning with current observations. Inflation started due to the conditions present in the early universe, particularly the high energy associated with the inflaton field, which created sufficient repulsive gravitational energy to drive the exponential expansion. Eventually, the inflaton field decayed into particles and radiation through a process known as reheating. This decay transferred the energy of the inflaton field into the nascent universe, ending the inflationary period. The universe then transitioned into the standard Big Bang expansion, gradually cooling and evolving to form atoms, stars, galaxies, and ultimately us. Thus, cosmic inflation offers a compelling narrative that not only addresses the initial uniformity and geometry of the universe, but also aligns with numerous observations. It transforms our understanding of the dynamics in the cosmos's earliest moments, providing an essential cornerstone for modern cosmology. In a Big Bounce scenario, the universe's origin story takes on a cyclical nature, contrasting with the singularity-driven Big Bang model. Instead of a singular explosive event marking the beginning of time and space, The Big Bounce envisions the universe undergoing an eternal series of expansions and contractions. The Big Bounce hypothesis suggests that the universe was previously in a contracting phase, compressing matter and energy into a highly dense and hot state. This ongoing contraction would eventually reach a minimum, where quantum gravitational effects become significant. At this critical juncture, the repulsive forces due to quantum gravity could prevent the universe from collapsing into a singularity, instead triggering a bounce that initiates a new expansion phase. During the contraction phase, gravitational forces pull everything closer together, and the temperature and density of the universe increase. As these conditions intensify, quantum effects in space-time would likely become predominant. Theoretically, these effects could generate a repulsive quantum pressure that opposes gravitational attraction, stopping the collapse and leading to the bounce. After the bounce, the universe would expand once more, with the high-energy conditions setting off processes analogous to those in the Big Bang model, including particle formation, nucleosynthesis, and the eventual formation of stars and galaxies. Some Big Bounce models also incorporate an inflationary period to explain the uniformity and flatness of the universe, similar to traditional Big Bang cosmology. The universe's cyclical nature in a Big Bounce framework offers a fascinating implication. The cosmos could be eternal, with no definite beginning or end. Each cycle of contraction and expansion could potentially erase detailed memories of previous cycles, ensuring that each universe iteration starts afresh. This perspective not only challenges our understanding of cosmic boundaries, but also prompts questions about the long-term evolution of physical laws and constants across cycles. Such a model remains highly speculative and is an area of active theoretical research, especially in the realm of quantum gravity and loop quantum cosmology. If validated through future cosmological data and observations, the Big Bounce could profoundly reshape our comprehension of the universe's true nature and its enigmatic origins. Baryon acoustic oscillations are a crucial aspect of understanding the large-scale structure of the universe and its expansion history. These oscillations are essentially sound waves that propagate through the hot, dense plasma of the early universe shortly after the Big Bang. Their observational signatures provide valuable information about the early universe's conditions and the nature of dark energy driving its accelerated expansion. In the immediate aftermath of the Big Bang, the universe was filled with a nearly homogeneous mixture of photons, electrons, and baryons. The intense heat and density allowed photons to effectively couple with baryons, creating a plasma. As the universe expanded and cooled, gravitational forces began drawing matter inward, while radiation pressure from photons resisted this compression, creating oscillations similar to sound waves. When the universe was around 380,000 years old, it cooled enough for protons and electrons to combine and form neutral hydrogen atoms, a period known as recombination. This decoupling of photons from baryons caused the cosmic microwave background radiation we observe today, and effectively froze the positions of these oscillations into the matter distribution of the universe. These frozen oscillatory patterns left an imprint in the distribution of galaxies and large-scale structures. BOs serve as a standard ruler for cosmologists. The characteristic scale of these oscillations, about 500 million light-years, provides a fixed reference by which distances in the universe can be measured. By analyzing the spatial distribution of galaxies and the pattern of BAOs, scientists can determine the rate at which the universe is expanding over time. Moreover, the precise measurement of BAOs contributes to our understanding of dark energy, the mysterious force driving the accelerated expansion of the universe. By mapping the universe's expansion history through BAOs, cosmologists can refine models of dark energy and assess its properties more accurately. This makes BAOs a powerful tool in modern cosmology, linking the physics of the early universe with observations of its large-scale structure and evolution. The apparent lack of antimatter in the observable universe is a significant puzzle in modern physics. According to the standard model of particle physics, the Big Bang should have produced equal amounts of matter and antimatter. However, when we look around, we observe a universe dominated by matter, with antimatter conspicuously scarce. One leading explanation for this discrepancy is a phenomenon known as baryogenesis, which occurred in the early universe. Baryogenesis refers to processes that produced a slight excess of baryons over antibaryons. Several mechanisms could be responsible for this asymmetry, such as CP violation. CP violation means that the laws of physics change slightly when particles are swapped with their antiparticles and their spatial coordinates are reversed. In simpler terms, particle interactions might not be completely symmetrical, leading to a small but significant imbalance in the amounts of matter and antimatter produced. Sakharov conditions, proposed by physicist Andrei Sakharov in 1967, offer criteria necessary for baryogenesis. These include baryon number violation, C and CP symmetry violations, and interactions out of thermal equilibrium. In the high-energy environment of the early universe, these conditions could have been satisfied, leading to processes where more matter than antimatter was generated. Another possibility involves asymmetries in the interactions at a fundamental level during the universe's very early stages. For instance, heavy particles that decayed shortly after the Big Bang might have produced slightly more matter than antimatter, tipping the balance in favor of a matter-dominated universe. Observations of cosmic rays and experiments in particle physics continue to search for signs of antimatter or processes that could explain this imbalance. Facilities such as the Large Hadron Collider and experiments like those at CERN are vital in probing these fundamental questions. While the exact mechanisms behind this matter-antimatter asymmetry remain uncertain, they hold the key to deepening our understanding of the universe's early moments and the fundamental laws governing its evolution. The cyclic nature of star formation in galaxies is driven by a continuous interplay between various processes that convert gas into stars and the eventual recycling of stellar material back into the interstellar medium. This stellar life cycle ensures that galaxies are not static, but dynamic systems where star formation can wax and wane over billions of years. One of the primary mechanisms that initiates star formation involves the gravitational collapse of dense regions within giant molecular clouds, which are vast reservoirs of coal gas and dust. When these clouds become unstable, possibly triggered by compressive forces such as shock waves from supernova explosions, galaxy collisions, or spiral density waves in spiral galaxies, they can fragment and collapse under their gravity. This leads to the formation of new stars in stellar nurseries. As stars age and evolve, particularly the massive ones, they end their lives in spectacular supernova explosions, releasing an immense amount of energy back into the surrounding space. These supernovae not only enrich the interstellar medium with heavier elements forged in their cores, but also generate shock waves that can compress nearby gas clouds, potentially triggering new rounds of star formation. This feedback loop, a stellar death reigniting new stellar births, helps sustain the cyclical nature of star formation. Additionally, galaxies can experience interactions and mergers with other galaxies or pass through intergalactic medium structures laden with gas. These encounters can trigger massive bursts of star formation by disturbing the galactic structure and funneling gas into the central regions, where it can cool and condense into new stars. This kind of event is known as a starburst and can significantly enhance a galaxy's star formation rate for a period. On longer timescales, the interplay of the galaxy's dynamic processes, such as the rotation of its disk, the influence of its spiral arms, and the presence of molecular clouds, contributes to periods of heightened and reduced star formation. Together, these mechanisms sculpt the ongoing cyclical creation and recycling of stars, making star formation an intrinsic characteristic of galactic evolution. Supermassive black holes, often found lurking in the centers of galaxies, exert a profound influence on their host galaxy's evolution through a variety of dynamic processes. These behemoths, with masses ranging from millions to billions of times that of the Sun, play a crucial role in regulating star formation shaping galactic structures and affecting the broader environment of the cosmos. One of the most significant ways supermassive black holes influence their galaxies is through feedback mechanisms, which primarily occur when these black holes accrete large amounts of matter. As material spirals into the black hole, it heats up and emits enormous amounts of energy in the form of radiation and powerful jets. This outpouring of energy can heat and expel gas from the galaxy's central regions, effectively shutting down new star formation by depriving it of the cold gas necessary for birth. These feedback processes can have dramatic effects on the galaxy's interstellar medium, not only inhibiting star formation, but also redistributing gas and dust throughout the galaxy. This can lead to the formation of distinctive structures such as active galactic nuclei, bright quasars, and relativistic jets extending far beyond the host galaxy, sculpting the larger-scale intergalactic environment. Supermassive black holes also influence their host galaxies during major galactic mergers. When two galaxies collide, their central black holes can eventually coalesce, releasing vast amounts of energy in gravitational waves. The merger of black holes can trigger intense starburst activity by funneling gas into the galaxy's central regions, simultaneously feeding the black holes and igniting rapid periods of star formation. This violent interplay aids in the transformation of galactic morphology, often reshaping spiral galaxies into more elliptical forms. Furthermore, the masses of supermassive black holes are observed to correlate closely with certain properties of their host galaxies, such as the velocity dispersion of stars in the galactic bulge, known as the M-sigma relationship. This correlation suggests a co-evolutionary process where the growth of the black hole and the galaxy influence each other, highlighting a deeper interconnected evolution. These myriad interactions showcase how supermassive black holes act as cosmic architects, orchestrating an array of processes that dictate the growth, structure, and life cycle of their host galaxies. By understanding these colossal entities, we gain insights into the broader narrative of galactic evolution across the universe's history. Reionization is a pivotal epoch in cosmological history, marking a major transition in the universe from an opaque state to one that is transparent and ionized. This event took place roughly several 100 million years after the Big Bang and represents the period when the first light sources began to ionize the hydrogen gas that filled the early universe. To understand reionization, we first need to recognize what came before it. After the Big Bang, the universe was a hot, dense plasma of subatomic particles. As it expanded and cooled, protons and electrons combined to form neutral hydrogen atoms in a process known as recombination, occurring around 380,000 years after the Big Bang. This event caused the universe to become transparent to radiation, allowing the cosmic microwave background to be observed today. However, neutral hydrogen atoms strongly absorb ultraviolet light, meaning that for the next several 100 million years, often referred to as the cosmic dark ages, the universe was filled with this neutral gas and lacked visible light sources. The epoch of reionization began when the first stars and galaxies formed, emitting substantial amounts of ultraviolet radiation. These early stars, likely massive and short-lived, along with proto-galaxies and possibly active galaxies hosting accreting black holes, produced an immense amount of ultraviolet light. This radiation was energetic enough to ionize hydrogen, meaning it could strip electrons from hydrogen atoms, turning them back into free protons and electrons. Gradually, these ionizing photons created bubbles of ionized gas around their sources. As more stars formed and galaxies evolved, these ionized bubbles grew and merged until the entire universe transitioned from a neutral to an ionized state. The reionization epoch had significant implications for the universe's evolution and the formation of cosmic structures. It allowed light to travel freely through space, making the universe fully transparent and permitting the formation of more complex structures such as galaxies and galaxy clusters. Studying reionization helps astronomers understand the nature of the first light sources and the timeline of cosmic evolution. Observations of the intergalactic medium, quasar light absorption spectra, and the cosmic microwave background provide crucial evidence about the timing and nature of reionization. By piecing together this epoch, scientists aim to shed light on how the first structures formed and evolved, ultimately painting a clearer picture of our universe's early history. Dark energy is one of the most mysterious components of our universe, comprising approximately 70% of the total energy. It is driving the accelerated expansion of the cosmos, pushing galaxies apart at an ever-increasing rate. But what if dark energy itself were to change over time? If dark energy evolves, its influence on the universe's expansion could either intensify or diminish. Should it strengthen, the acceleration of cosmic expansion would increase dramatically, potentially leading to a future where galaxies move so far apart that distant galaxies become invisible and unreachable, even with the most powerful telescopes. This scenario, often referred to as the Big Rip, suggests that the fabric of space-time could eventually be torn apart, disintegrating galaxies, stars, planetary systems, and even atomic structures. Conversely, imagine if dark energy diminishes over time. The expansion of the universe could slow, halting the current accelerated pace. This deceleration might ultimately reverse the expansion, culminating in a big crunch where all matter and energy in the universe collapse back into an extremely dense state, possibly leading to the rebirth of the universe in a new Big Bang. The precise nature of dark energy remains one of cosmology's greatest enigmas. Understanding how it might evolve demands deeper observations and refined theories, potentially opening doors to aspects of physics that are currently beyond our grasp. Whether dark energy will forever accelerate our universe or lead to an entirely different fate is a profound question that continues to challenge our understanding, inspiring scientists worldwide to uncover its secrets. Quark-gluon plasma is a state of matter believed to have existed just microseconds after the Big Bang. In this extreme environment, quarks and gluons, the fundamental building blocks of protons and neutrons, are not confined into particles, but move freely in a hot, dense soup. To visualize this, imagine a liquid with particles buzzing around at nearly the speed of light, far beyond our everyday experience. Scientists have succeeded in recreating this primordial state momentarily in high-energy particle collisions, such as those conducted at the Large Hadron Collider. Conditions in these experiments reach temperatures over 1 trillion degrees Celsius, briefly allowing quarks and gluons to escape their usual prison within atoms. In the cosmos today, quark-gluon plasma is likely to exist in the hearts of the most massive neutron stars, objects so dense that they are essentially giant atomic nuclei. Theoretical models suggest that under the immense pressure at a neutron star's core, matter could revert to this earlier state. These stars serve as natural laboratories, offering clues to conditions that are otherwise impossible to achieve on Earth. Understanding quark-gluon plasma not only provides a glimpse into the universe's embryonic moments, but also helps unravel the mysteries of matter under extreme conditions. The behavior of this exotic state influences our comprehension of the universe's birth, evolution, and the ultimate fate of the densest objects in the cosmos. Each discovery brings us one step closer to piecing together the puzzle of our universe's fundamental nature. Neutron stars are some of the densest objects in the universe, resulting from the gravitational collapse of massive stars after supernovae. Within these stellar remnants might lie an even more exotic form of matter known as strange matter, a phase of quark matter containing not just up and down quarks, but also strange quarks. The presence of strange matter could profoundly affect the properties and structure of neutron stars, potentially giving rise to what are termed strange stars. Unlike conventional neutron stars, these strange stars might be more stable and denser, as the addition of strange quarks allows matter to be packed even tighter. This could result in smaller radii for stars of the same mass compared to neutron stars composed solely of up and down quarks. One intriguing possibility is the existence of strangelets, small droplets of strange matter that could convert regular neutron star matter into strange matter upon contact. If a neutron star were punctured by a strangelet, the conversion process could propagate rapidly, leading to a complete transition of the star into a strange star. The search for strange matter within neutron stars remains a significant scientific endeavor. Observing unique gravitational waves from neutron star mergers or detecting specific signals from pulsars might provide evidence supporting the existence of strange matter. Such discoveries would not only revolutionize our understanding of neutron stars, but also offer insights into the behaviors and properties of matter at the most extreme states, pushing the boundaries of modern physics. Symmetric and asymmetric matter play pivotal roles in our understanding of the universe, particularly when it comes to the disparity between matter and antimatter. Symmetric matter suggests that equal amounts of matter and antimatter should have existed after the Big Bang. However, the universe we observe is overwhelmingly made of matter, indicating an imbalance known as baryon asymmetry. Theoretical physics posits that during the early moments of the universe, a mechanism caused this imbalance, resulting in the dominance of matter over antimatter. If symmetric and asymmetric matter coexisted, it would imply that some conditions favored the creation or survival of matter, skewing this balance in favor of the material universe we inhabit. Additionally, the concept of symmetric and asymmetric matter extends into particle physics and cosmology, hinting at new physics beyond the standard model. For example, the study of charge parity violation explores how certain reactions might have favored matter over antimatter. CP violation in processes involving particles like neutrinos might provide clues to this asymmetry, offering insight into an essential part of cosmic history. Exploring this asymmetry has deep implications for understanding the universe's evolution. It connects to questions about the matter genesis, the behavior of fundamental particles, and the nature of the forces shaping the cosmos. Each piece of evidence concerning symmetric and asymmetric matter brings us closer to comprehending why the universe exists in its current form, shaped by the remnants of a cosmic dance between matter and antimatter billions of years ago. Ultra-diffuse galaxies present an intriguing puzzle for astronomers. These galaxies, often as large as the Milky Way, are exceptionally faint and spread out, containing far fewer stars. Their very existence challenges our traditional understanding of galaxy formation and evolution. One explanation for their unusual properties lies in their potential composition. Many of these galaxies appear to be dominated by dark matter, the unseen substance that is prevalent throughout the universe. Despite their sparse stellar populations, these galaxies can maintain structural integrity if they possess massive dark matter halos. This could explain why such vast, faint galaxies remain intact despite their apparent lack of stars and other visible matter. Another possibility involves their formation history. Ultra-diffuse galaxies might have formed in regions with limited star-forming material or experienced events that prevented significant star formation, such as supernova blasts or tidal interactions with other galaxies. These interactions could strip them of their gas, halting further stellar development and leaving behind a spread-out collection of stars. Interestingly, some ultra-diffuse galaxies defy expectations by housing relatively rich star clusters or even supermassive black holes. These features suggest a diverse range of formation processes and evolutionary paths, hinting that these galaxies might be survivors of ancient cosmic upheavals or mergers. Each discovery adds layers to our understanding, compelling astronomers to refine models of galaxy formation and adapt our theories to accommodate the fascinating diversity of galactic structures in the universe. The concept of dark fluid is an attempt to unify dark matter and dark energy into a single framework. While dark matter constitutes about 27% of the universe's energy density and dark energy accounts for about 70%. Dark fluid theory proposes that a single entity might manifest differently under various cosmic conditions. Dark fluid might behave like dark matter in regions of high density, such as galaxies and galaxy clusters. This would help explain the gravitational effects we observe that cannot be accounted for by visible matter alone. For instance, the rotational speeds of galaxies and the movement of galaxy clusters hint at an unseen mass that dark matter is thought to provide. Conversely, in the vast, low-density stretches between galactic structures, dark fluid could exhibit properties similar to dark energy, driving the accelerated expansion of the universe. In these sparse regions, the repulsive force akin to dark energy's influence could dominate, pushing galaxies apart and shaping the universe's large-scale structure. If proven true, dark fluid theory would significantly simplify our understanding of the cosmos by reducing the need for two separate mysterious substances. However, verifying this idea requires extensive observational and theoretical work, possibly involving precise measurements of cosmic expansion and galactic behaviors under varied conditions. If successful, uncovering the nature of dark fluid could unify our understanding of two of the most enigmatic components of the universe, offering profound insights into its fundamental workings. Mirror matter, a fascinating theoretical concept, posits that every particle of ordinary matter has a corresponding mirror twin. These mirror particles would mirror the properties of their counterparts but would interact primarily through a mirror version of fundamental forces. This idea extends symmetry in nature, suggesting that a hidden sector of the universe might exist alongside our familiar world. If mirror matter exists, it could fundamentally alter our understanding of dark matter. Dark matter's elusive nature has puzzled scientists, being detectable only through gravitational effects. Mirror matter, with its invisible particles, might account for dark matter's unseen mass. This would mean that galaxies are embedded in halos of mirror matter, contributing gravitational pull without emitting light. The implications go even further. Mirror matter could influence cosmic events, potentially resulting in novel astrophysical phenomena. For example, interactions between ordinary and mirror matter might generate unusual signatures in cosmic microwave background radiation, or exotic forms of gravitational lensing, where light from distant stars bends in unexpected ways. Such discoveries would offer new pathways to identify and study this hidden matter. Detection and confirmation of mirror matter require innovative experimental approaches and high-precision measurements. From deep underground detectors to space-based observatories, the quest to uncover mirror matter's secrets could open new chapters in physics. Each step towards understanding mirror matter not only deepens our grasp of the universe's composition, but also challenges the boundaries of modern scientific theories, promising a richer and more intricate cosmic tapestry than we ever imagined. Bose-Einstein condensates represent one of the most extraordinary states of matter, where particles known as bosons are cooled to temperatures near absolute zero. Under these extreme conditions, the particles occupy the same quantum state, essentially behaving as a single quantum entity. This phenomenon allows scientists to observe quantum mechanical effects on macroscopic scales, unveiling aspects of quantum physics that are usually confined to the microscopic world. Taking Bose-Einstein condensates into space opens up unprecedented research opportunities. In the microgravity environment of space, the normally fleeting duration of Bose-Einstein condensates on Earth is significantly extended. This grants researchers more time to study their properties and behavior. Experiments conducted on the International Space Station have already created Bose-Einstein condensates, significantly expanding our understanding of quantum mechanics. Bose-Einstein condensates in space can also help refine our understanding of fundamental physics. They could potentially serve as sensitive detectors for gravitational waves or other disturbances in space-time. By observing how these quantum states respond to external influences, scientists can test aspects of general relativity and quantum theory in ways not possible on Earth. In the vast silence of space, Bose-Einstein condensates might unravel mysteries that could lead to groundbreaking technological advancements. From highly precise atomic clocks to innovations in materials science and quantum computing, the insights gained from Bose-Einstein condensates in microgravity pave the way for future scientific and practical applications. Each experiment in space brings us closer to mastering the quantum realm, showing just how interconnected and boundless our quest for knowledge truly is. Cosmic strings are theoretical one-dimensional defects in the fabric of space-time that might have formed during the early moments of the universe. These cosmic relics, essentially thin but extremely dense tubes of energy, are thought to stretch across vast regions of the cosmos. If they exist, cosmic strings could play a crucial role in shaping the large-scale structure of the universe, including the formation of galaxies. The presence of cosmic strings could create gravitational wells that attract surrounding matter. As cosmic strings move through space, they could leave behind wakes of densified matter, serving as seeds around which galaxies and galaxy clusters form. This gravitational influence might accelerate the aggregation of gas and dark matter, leading to the faster formation of proto-galactic structures compared to regions without cosmic strings. Moreover, cosmic strings might also produce distinctive observational signatures, such as peculiar gravitational lensing effects. When light from distant stars or galaxies passes near a cosmic string, the energy from the string can warp spacetime, bending the light in unique ways that differ from traditional gravitational lenses like galaxy clusters. Detecting such lensing patterns could provide direct evidence of cosmic strings and help validate their impact on galaxy formation. The existence of cosmic strings would significantly enhance our understanding of the universe's evolution. By providing foundational structures around which matter can congregate, they could explain the observed filamentary network of galaxies, often referred to as the cosmic web. Studying cosmic string-induced phenomena could also shed light on the nascent universe's conditions, offering a window into processes occurring mere moments after the Big Bang. As our observational techniques continue to advance, the potential discovery of cosmic strings would represent a profound leap forward in cosmology, connecting theoretical predictions with cosmic reality. Dark atoms and dark photons emerge from the intriguing possibility that dark matter is composed of particles that mirror the behaviors of particles in the visible universe, but interact through forces we have yet to detect. This framework proposes that dark matter could be organized similarly to ordinary matter, forming complex structures like atoms, albeit invisibly. Dark atoms might consist of dark protons and dark electrons bound together by dark photons. Dark photons would function as the mediators of the electromagnetic force in the dark sector, analogous to how ordinary photons act in visible matter. These dark atoms, while not interacting with ordinary light or electromagnetic forces, could still exert gravitational effects, making them detectable through their influence on galaxy rotation curves and cosmic structure formation. The behavior of dark atoms and dark photons could provide insights into the microcosm of dark matter. For instance, if dark photons are present, they might lead to observable phenomena such as dark electromagnetic forces or even dark matter interactions that occasionally produce detectable signals in sensitive detectors. Experiments designed to capture these rare events could offer clues to the existence and properties of these unseen particles. Exploring the nature of dark atoms and dark photons requires innovative theoretical work and cutting-edge experimental techniques. Observational anomalies, such as unusual particle interactions or unexpected gravitational effects, might serve as indicators. Unraveling the properties and interactions of dark atoms and dark photons would significantly advance our understanding of dark matter, offering a clearer picture of the universe's unseen components and potentially revolutionary insights into the fundamental workings of nature at its deepest levels. Primordial black holes, hypothesized to have formed in the chaotic environment of the early universe, well before stars and galaxies came into existence, could significantly influence our understanding of cosmic evolution. Unlike stellar black holes formed from collapsing stars, Primordial black holes might originate from density fluctuations in the infant universe, collapsing directly under their own gravity. If primordial black holes exist, they could provide substantial insights into the nature and behavior of dark matter. Some theories propose that these small black holes could make up a portion or even all of the elusive dark matter. Their gravitational pull, while not luminous, would influence the movement of galaxies and the formation of large-scale structures. This would offer a tangible component to explain the unseen mass that dark matter signifies. Moreover, primordial black holes might be pivotal in explaining phenomena such as the reionization of the universe, a period when the first sources of light ionized intergalactic hydrogen. As they interact with their surroundings, these black holes could emit radiation and energetic particles, contributing to the heating and ionizing of the early universe, and thus playing a role in the emergence of the first stars and galaxies. Their existence could also shed light on the observed spectrum of gravitational waves. The collision or merger of primordial black holes would release gravitational waves detectable by observatories like LIGO and Virgo. Distinguishing these signals from those produced by stellar mass black holes could provide unique insights into the early universe's conditions and the processes that governed its evolution. The detection and study of primordial black holes would address fundamental questions about the universe's birth and growth. Establishing their presence would not only enhance our understanding of dark matter and cosmic history, but also open new avenues in high-energy astrophysics, revealing layers of cosmic dynamics that have shaped our universe since its inception. The immense magnetic fields observed in some galaxy clusters pose a fascinating question in astrophysics. These fields, spanning millions of light-years, significantly influence the behavior of hot gas and cosmic rays within the clusters. Understanding their origin involves several mechanisms and processes that come into play over cosmic timescales. One primary contributor to these large-scale magnetic fields is the dynamo mechanism. This process involves the motion of conducting material, such as the ionized gases present in galaxy clusters. As these gases move, they can amplify existing magnetic fields through the generation of electric currents. Over billions of years, the dynamo effect can transform initially weak magnetic fields into the colossal structures observed. Another important factor is turbulence within the intracluster medium. Galaxy clusters contain vast amounts of superheated gas, often the result of galaxy collisions and supernova explosions. These events stir the gas, creating turbulent motions that can stretch and fold magnetic field lines, causing them to intertwine and amplify. This turbulent motion acts like a cosmic mixing machine, enhancing the magnetic field strength and distributing it over large areas. Additionally, primordial magnetic fields generated during the early universe could serve as seeds for the observed fields in galaxy clusters. During the epoch of cosmic inflation, quantum fluctuations might have produced tiny magnetic fields. As the universe expanded and structures formed, these primordial fields could be stretched and amplified through processes such as accretion and mergers, contributing to the magnetic environments we observe today. Understanding these magnetic fields requires multifaceted approaches, combining observations from radio telescopes, X-ray satellites, and numerical simulations. Each discovery adds a piece to the puzzle, revealing the intricate interplay of cosmic forces. The study of these magnetic fields not only informs us about the rich dynamics within galaxy clusters, but also offers insight into the broader magnetic history of the universe itself, underscoring the profound influence of magnetism in cosmic evolution. Cosmic magnetic fields play a crucial role in shaping the journey of high-energy particles across the universe. These fields, spanning interstellar and intergalactic spaces, act as a cosmic web through which particles must navigate, profoundly affecting their trajectories and behaviors. Firstly, magnetic fields can deflect the paths of charged particles, such as cosmic rays. As these high-energy particles encounter magnetic fields, They spiral around the field lines instead of traveling in straight lines. This spiraling motion significantly increases the distance they travel, effectively scattering them and making their origins more diffuse. This deflection helps explain why pinpointing the exact source of cosmic rays is challenging and has led to the extensive search for their origins. Magnetic fields also impact the energy and velocity of these particles. In regions of stronger magnetic fields, particles can be trapped and spiral incessantly, losing energy through synchrotron radiation, a type of electromagnetic radiation emitted when charged particles accelerate in magnetic fields. This phenomenon is observed in astrophysical environments like supernova remnants and active galactic nuclei, where intense magnetic fields shape the radiation spectra we detect. Oh, gosh! Additionally, magnetic fields magnetize the interstellar and intergalactic mediums, creating barriers and channels that influence particle propagation. In dense regions, such as galaxy clusters, enhanced magnetic fields can essentially funnel particles along specific pathways, concentrating them in certain areas while restricting their movement in others. This can lead to the formation of cosmic ray hotspots and regions with higher levels of radiation, impacting the local environment and potentially affecting star formation rates and galactic evolution. The influence of magnetic fields on high-energy particles is a fundamental aspect of cosmic astrophysics. Detailed observation and modeling of these interactions enhance our understanding of the high-energy universe, offering clues about the processes in the most energetic and dynamically active regions of space. As we uncover the mysteries of these magnetic interactions, we're not only learning about particle physics on a grand scale, but also about the vast and invisible forces shaping the cosmos. The magnetized filaments near the galactic center are among the most enigmatic structures observed in our Milky Way. These slender, elongated features stretching tens of light years are composed of highly magnetized plasma, and their origins have intrigued astronomers for decades. One leading theory suggests that these filaments are the result of powerful magnetic fields anchored to the supermassive black hole at the galaxy's core, known as Sagittarius A star. The immense gravitational forces and energetic processes surrounding this black hole could twist and stretch the magnetic field lines, creating the filamentary structures. Active regions near the galactic center are prone to dynamic phenomena, including powerful stellar winds and outflows from the black hole itself, which could drive the formation of these magnetic strands. Another possible origin lies in the interaction between cosmic rays and the ambient magnetic field. Near the galactic center, increased cosmic ray activity can induce currents that amplify and organize magnetic fields into filaments. This mechanism would explain why the filaments are highly magnetized, and suggests that they act as conduits or highways for cosmic rays, shaping their distribution in this turbulent region. Moreover, the formation of these filaments could be linked to the complex dynamics of star formation and supernova explosions near the galactic center. Massive stars in this region eventually explode as supernovae, releasing shock waves that can compress and stretch the magnetic field lines. The interplay between shock waves and existing magnetic fields could give rise to the long, thread-like structures observed. The study of these magnetized filaments involves intricate observations using radio telescopes and advanced simulations. Understanding their origins helps illuminate the broader magnetic architecture of our galaxy and the energetic processes at its core. Each filament serves as a cosmic laboratory, offering insights into the fundamental interactions between magnetic fields, cosmic rays, and the dense, dynamic environment surrounding the heart of the Milky Way. Magnetic fields are fundamental to the process of star formation and their subsequent evolution. Their influence spans from the earliest stages of molecular cloud collapse to the lifespan and even the death of stars. During the initial stages of star formation, magnetic fields play a crucial role in the collapse of molecular clouds, vast regions of cold gas and dust. These clouds must overcome their inherent thermal pressure and turbulence to form dense cores where stars can begin to form. Magnetic fields help regulate this collapse by providing additional pressure that can slow down the process, leading to more gradual and controlled contraction of the cloud. This balance between gravity, thermal pressure, and magnetic forces shapes the rate and efficiency of star formation within these clouds. Once a star begins to form, magnetic fields continue to influence its development by guiding the accretion of material. Young stars or protostars often gather mass through accretion disks, rotating disks of gas and dust that feed the growing star. Magnetic fields in these disks can channel material onto the protostar via magnetic funneling, impacting the star's eventual mass and angular momentum. These fields also drive powerful outflows and jets that clear away excess material, helping to regulate the amount of mass that ultimately forms the star. As stars mature, magnetic fields become pivotal in generating stellar activity, including phenomena like sunspots, solar flares, and stellar winds. For instance, our Sun's magnetic field is responsible for the 11-year solar cycle marked by increases and decreases in solar activity. Magnetic fields in stars twist and reconnect, releasing enormous amounts of energy that influence the star's outer layers and its surrounding space. This activity can also affect planetary systems, making magnetic fields a critical factor for planetary habitability. Finally, in the latter stages of a star's life, magnetic fields can dictate the nature of its death. For example, in massive stars, magnetic fields can influence the dynamics of supernova explosions and the formation of neutron stars or black holes. In lower mass stars, magnetic fields help shape the evolution of white dwarfs. In all these cases, magnetic fields interact with the stellar material, guiding its final distribution and the remnants left behind. Magnetic fields are woven into the very fabric of stellar life cycles, from birth to death. Understanding their complex interactions with stellar and interstellar matter provides key insights into the fundamental processes that govern the cosmos, revealing the intimate connection between magnetism and the life stories of stars. Magnetic anomalies in exoplanets are fascinating and can be attributed to a variety of causes. One primary reason is the dynamic interior of these distant worlds. Just like Earth has a magnetic field generated by the movement of molten iron within its core, exoplanets may have similar processes at play. The rotation and convection currents within an exoplanet's liquid metallic core can create powerful magnetic fields. If these currents are irregular or influenced by other factors, they can produce the unusual magnetic anomalies that scientists observe. Furthermore, the interaction between an exoplanet's magnetic field and the stellar wind from its host star can also play a significant role. This interaction can distort the magnetic field lines, leading to complex magnetic behaviors. Some exoplanets are much closer to their stars than Earth is to the Sun, meaning the intense solar wind can have a greater impact, compounding the anomalies. Planetary composition and rate of rotation also influence these magnetic fields. For instance, an exoplanet with a diverse mix of conducting materials in its core might show more erratic magnetic behavior. Additionally, the rate at which a planet spins affects the dynamo process within the core. Rapid rotation can amplify magnetic activities, while slower rotation could lead to reduced or differently structured fields. Lastly, external cosmic phenomena such as nearby stellar activity or interstellar magnetic fields can induce anomalies. Nearby supernova, binary star systems, or interaction with interstellar clouds could influence the magnetic environment of an exoplanet, leading to observations of magnetic fields that deviate from expected models. Understanding these anomalies helps us learn not only about the exoplanets themselves, but also about the broader interactions within their planetary systems. Intergalactic magnetic fields play a crucial role in shaping the universe's large-scale structure by influencing the behavior of cosmic matter and the dynamics of galaxy formation. These magnetic fields, though relatively weak compared to those of stars or planets, extend across vast distances and can impact the motion of charged particles in space. As charged particles move through these magnetic fields, they experience a force that alters their trajectories, affecting the formation and evolution of cosmic structures. These magnetic fields can impact the distribution of gas and dust in intergalactic space. As gas clouds traverse through magnetic fields, the fields can induce turbulence, leading to variations in density and temperature within these clouds. Such turbulence can affect the rate at which gas cools and collapses to form new stars and galaxies. These processes, in turn, influence the spacing and alignment of galaxies, contributing to the overall pattern we observe in the cosmic web. Moreover, intergalactic magnetic fields also interact with cosmic rays, high-energy particles that travel through the universe. As cosmic rays travel through these fields, their paths are bent and twisted. This bending can spread the cosmic rays over larger areas, spreading energy throughout intergalactic space and potentially triggering bursts of star formation or altering existing magnetic fields aligned with ancient cosmic structures. And furthermore, these fields might have formed in the early universe, potentially guiding the distribution of matter and influencing how galaxies clustered together over billions of years. By studying these magnetic fields, scientists can gain insights into the primordial conditions of the universe and how they shaped the large-scale structures we see today. As our understanding deepens, we continue to reveal the intricate tapestry woven by these invisible yet influential intergalactic forces. Magnetic reconnection events in cosmic plasmas are significant because they release massive amounts of energy and can dramatically alter the behavior of celestial bodies and phenomena. These events occur when magnetic field lines that are oppositely directed come into close contact and suddenly rearrange themselves, breaking and reconnecting in new combinations. This realignment releases stored magnetic energy in the form of heat, light, and particle acceleration, making magnetic reconnection a powerful and dynamic process. In the Sun's atmosphere, for example, magnetic reconnection is responsible for solar flares and coronal mass ejections, which are some of the most energetic events observed in our solar system. These solar flares can release energy equivalent to millions of hydrogen bombs and send charged particles hurtling into space at nearly the speed of light. When these particles reach Earth, they can disturb our planet's magnetic field, potentially disrupting communication systems, satellites, and power grids. Beyond our solar system, magnetic reconnection plays a crucial role in the environments around neutron stars and black holes. In these extreme conditions, the intense gravitational and magnetic fields can cause magnetic reconnection to occur at an incredibly energetic scale. This process can generate powerful jets of particles that shoot out at nearly the speed of light, becoming some of the brightest sources in the universe. These jets can influence the formation of stars and the growth of galaxies, spreading energy across vast distances. Magnetic reconnection is also important in shaping the behavior of interstellar and intergalactic medium, the spaces between stars and galaxies filled with plasma. By converting magnetic energy into kinetic and thermal energy, these events help to maintain the turbulent nature of these plasmas. This in turn affects the cooling rates of gas, the formation of new stars, and the overall evolution of galaxies. Understanding magnetic reconnection helps astronomers and physicists not only to predict space weather events that can affect our technology, but also to comprehend fundamental processes that drive the dynamics of the universe. These insights contribute to our broader knowledge of cosmic phenomena and the physical laws that govern the cosmos. Magnetic fields significantly influence the behavior of interstellar dust and gas, shaping the formation and evolution of cosmic structures. These fields permeate much of the universe, threading through star-forming regions, nebulae, and the vast expanses between stars. They interact with the charged particles within the dust and gas, affecting their motion, condensation, and how they clump together. In star-forming regions, magnetic fields provide a balancing force against gravity. As gas clouds begin to collapse under their own gravitational attraction to form new stars, the magnetic fields can slow down this collapse by exerting pressure on the charged particles within the gas. This magnetic support can lead to the formation of filamentary structures within the clouds, a common feature observed in star-forming regions. It helps to regulate the rate of star formation, preventing the gas from collapsing too quickly and allowing for a more gradual and sustained creation of stars over time. Magnetic fields also streamline the flow of interstellar dust and gas. By aligning charged particles along the magnetic field lines, they can create ordered patterns within otherwise turbulent clouds. This alignment can affect the polarization of light passing through interstellar dust, providing astronomers with a way to map the magnetic fields by observing the light from distant stars. These observations can offer clues about the orientation and strength of magnetic fields in various regions of our galaxy. Additionally, in the broader context of the interstellar medium, magnetic fields can trap cosmic rays and influence their propagation. These high-energy particles are funneled along magnetic field lines, affecting the thermal and ionization states of the interstellar gas. This interaction can alter the chemistry of the gas, influencing the formation of complex molecules that are precursors to life. Ultimately, magnetic fields help to sculpt the cosmic landscape, from the smallest scales of individual stars to the grand scale of entire galaxies. By understanding how these forces interact with and direct the behavior of interstellar dust and gas, scientists can piece together the intricate processes that govern the evolution and structure of the universe. Primordial magnetic fields are theorized to have been generated in the early universe, potentially during or shortly after the Big Bang. These fields are believed to be incredibly ancient and may have laid the groundwork for the magnetic fields observed in galaxies and clusters today. Understanding their nature is crucial for unraveling the origins of cosmic magnetism and its influence on the evolution of large-scale structures in the universe. In the moments right after the Big Bang, various processes could have produced these primordial magnetic fields. During a period known as cosmic inflation, when the universe expanded exponentially, quantum fluctuations, tiny random variations in density and energy, might have been stretched to cosmic scales, creating seed magnetic fields. Another possibility is that these fields emerged as the universe cooled and fundamental forces split from one another, a process known as phase transitions. Once formed, these primordial magnetic fields would have been relatively weak but pervasive throughout the early universe. As the universe expanded and galaxies began to form, these primordial fields could have been amplified and shaped by astrophysical processes. For instance, as gas clouds collapsed to form the first stars and galaxies, the movement and turbulent flows of ionized gas would stretch and twist the magnetic field lines, increasing their intensity. This amplification through a cosmic dynamo process continues to build up the magnetic fields observed today in stars, planets, and galaxies. One fascinating aspect of primordial magnetic fields is their potential to leave imprints on the cosmic microwave background radiation, the afterglow of the Big Bang. These imprints can appear as slight variations in temperature or polarization patterns, providing a valuable tool for astronomers to probe the early universe. By studying these imprints, scientists hope to gain insights into the properties of primordial magnetic fields, such as their strength and structure, and thereby better understand the fundamental processes that shaped the universe. Primordial magnetic fields, if they exist, bridge the gap between the birth of the universe and the magnetic phenomena we observe in the cosmos today. They provide a critical piece of the puzzle in our quest to understand the origins and evolution of the universe's magnetic landscape, revealing new layers of complexity in the cosmic story. Magnetic fields play a pivotal role in shaping and powering the jets produced by active galactic nuclei, commonly associated with supermassive black holes at the centers of galaxies. These jets are some of the most spectacular and energetic phenomena in the universe, capable of ejecting particles at nearly the speed of light over distances spanning millions of light years. At the heart of an active galactic nucleus lies a supermassive black hole whose immense gravitational pull draws in nearby matter, forming an accretion disk of intensely heated gas and plasma. As this material spirals inward, it generates powerful magnetic fields through rapidly moving charged particles. These magnetic fields can become twisted and amplified by the rotation of both the black hole and the disk, forming a magnetic structure that extends far from the black hole. The role of these magnetic fields is crucial in launching and collimating the jets. They act much like a cosmic accelerator, converting rotational energy from the black hole and the accretion disk into kinetic energy that propels particles outward. This process, known as the Blandford-Zanejek mechanism, involves the magnetic fields threading through the black hole's event horizon and extracting energy to launch the jets. Additionally, the twisted field lines confine and direct the outflow of particles, ensuring that the jets remain narrow and focused over vast distances. As the jets travel through interstellar and intergalactic space, magnetic fields continue to influence their behavior. The fields provide stability against instabilities that might otherwise cause the jets to dissipate or kink. They can also interact with the ambient medium, causing shocks and particle acceleration that emit radiation observable across the electromagnetic spectrum, from radio waves to gamma rays. This radiation provides valuable diagnostic tools for astronomers to study the properties of both the jets and the magnetic fields governing them. Magnetic fields not only power and sustain these jets, but also have significant implications for their impact on galaxy evolution. When these jets collide with interstellar gas, they can trigger or suppress star formation, thereby influencing the evolutionary pathways of galaxies. By understanding how magnetic fields regulate the dynamics of jets from active galactic nuclei, scientists can gain deeper insights into the complex interplay between black holes and their host galaxies, shedding light on the broader mechanisms driving cosmic evolution. Life evolving in the methane seas of Titan-like worlds would likely be vastly different from life as we know it on Earth. Titan, Saturn's largest moon, has a thick atmosphere rich in nitrogen and methane, and its surface features lakes and seas of liquid methane and ethane. These conditions pose a unique set of challenges and opportunities for the development of life. In place of water, organisms on Titan-like worlds would use liquid methane as a solvent for biochemical reactions. On Earth, water's polar nature supports a wide range of chemical interactions fundamental to life. Methane, being non-polar, would require a completely different set of biochemistry. Hypothetically, life might rely on cell membranes composed of materials that function well in liquid methane, such as those using more stable, less reactive molecules that can sustain integrity in such cold temperatures. Life in these methane seas would also need to find alternative energy sources. On Earth, many organisms rely on photosynthesis, converting sunlight into chemical energy. However, Titan lies far from the sun, receiving only a fraction of the sunlight Earth gets. Thus, Titan-like life forms would likely harness chemical energy instead, possibly through chemosynthesis. Organic molecules on Titan could react with hydrogen or acetylene, both present in its atmosphere, to produce energy. This chemosynthetic process could sustain ecosystems much like hydrothermal vent communities on Earth's ocean floors, where sunlight is absent and life depends on energy from chemical reactions. Another interesting consideration is how these organisms would manage their metabolism and reproduction in the extremely low temperatures of Titan, which average around -290 degrees Fahrenheit. Enzymes and other biological molecules would need to be adapted to function at such frigid temperatures without denaturing or freezing. These adaptations could include more rigid molecular structures that resist cold-induced brittleness or metabolic pathways that operate efficiently at these low energies. Exploring the potential for life in the methane seas of Titan-like worlds expands our understanding of what conditions can support life. This broadens our search for life beyond Earth and offers a rich field of study for astrobiology, challenging our assumptions about the limits of life and encouraging us to consider the diverse possibilities that the universe may hold. Subsurface oceans on icy moons, such as Jupiter's Europa and Saturn's Enceladus, offer tantalizing possibilities for the existence of life. These hidden oceans are shielded by thick ice crusts, but underneath lies vast amounts of liquid water, kept from freezing by the gravitational interactions with their parent planets, which generate heat through tidal forces. One of the most significant factors is the presence of liquid water, which is crucial for life as we know it. Water acts as a universal solvent, supporting complex chemical reactions necessary for biological processes. The discovery of water plumes erupting from these moons, such as the geysers on Enceladus, suggests active geological activity, which could provide energy sources necessary for sustaining life. Energy is essential for driving life processes, and in these subsurface oceans it might come from hydrothermal vents on the ocean floors. On Earth, such vents harbor rich ecosystems sustained by chemosynthesis, where microorganisms derive energy from chemical reactions, such as those involving hydrogen sulfide and other minerals. Similar processes could support life in the oceans of icy moons, with geothermal activity providing the needed heat and nutrients. Moreover, these oceans could contain the essential building blocks of life. Organic molecules, such as simple hydrocarbons, amino acids, and sugars, have been found on some of these moons. While the concentration and complexity of these molecules in subsurface oceans are still under study, their presence raises the prospects for life. It is possible that these molecules formed through chemical reactions within the moon's oceans or were delivered by comets and meteorites over time. Studying these potential extraterrestrial environments for signs of life involves future missions that will aim to penetrate the ice crust or analyze the composition of water plumes more comprehensively. By doing so, scientists hope to detect direct or indirect evidence of biological activity. The prospect of life in these hidden oceans provides a profound glimpse into the potential diversity of life in the universe and challenges our understanding of where and how life can thrive. Life adapting to the extreme radiation environments around red dwarf stars would need to develop unique survival strategies, as these stars emit powerful bursts of radiation and possess volatile space weather. Despite their variability, red dwarf stars, also known as M-dwarfs, are the most common stars in our galaxy, making them prime targets in the search for extraterrestrial life. One possible adaptation is the development of robust biological mechanisms to repair DNA and other vital molecules damaged by radiation. On Earth, some extremophiles already exhibit such capabilities. For instance, the bacterium Deinococcus radiodurans can withstand high levels of radiation by efficiently repairing its DNA. Organisms on planets orbiting red dwarf stars might evolve similar, if not more advanced, repair mechanisms to cope with the constant bombardment of ultraviolet and X-ray radiation. Another strategy could involve protective biostructures or behaviors. Life forms might thrive underground or underwater, where they would be shielded from the majority of harmful radiation. Subsurface habitats, whether in soil, rock, or under ice, could provide a safe environment while still allowing access to necessary resources. Alternatively, these organisms might live within the solid crust of their home planet, emerging only periodically or evolving metabolic pathways that are less dependent on direct sunlight. Organisms might also evolve biochemical shields or pigments that absorb or deflect harmful radiation. Such pigments could serve a dual purpose, both protecting cells from radiation damage and potentially harnessing light for photosynthesis. This process might not be identical to terrestrial photosynthesis, but could still provide the energy necessary for survival. These pigments might appear in various colors, depending on the specific wavelengths of radiation they are designed to block or use efficiently. Another intriguing possibility involves symbiotic relationships. Organisms might form symbioses with other life forms that produce protective compounds or structures, enhancing their resilience against radiation stress. Symbiotic partnerships could facilitate a division of labor, where some organisms focus on protection while others specialize in energy production or resource acquisition, thereby increasing their collective chance of survival. Overall, life around red dwarf stars would need to be highly adaptable and resourceful, finding innovative ways to mitigate the challenges posed by extreme radiation environments. These adaptations could vastly differ from those observed on Earth, emphasizing the incredible diversity and resilience that life might exhibit across the cosmos. Silicon-based life, as an alternative to carbon-based life, might exhibit unique and fascinating forms adapted to the extreme environments found in the cosmos. Silicon, like carbon, can form multiple bonds and create complex molecules, making it a potential candidate for the biochemical basis of life. However, silicon's chemistry differs in ways that would shape the structure and behavior of silicon-based organisms profoundly. In high-temperature environments, such as those found near volcanic vents on planets or moons, or on worlds with harsh cosmic radiation, silicon-based life could thrive where carbon-based life cannot. Silicon-silicon bonds are more stable at higher temperatures than carbon-carbon bonds, lending silicon-based biochemistry a relative advantage in scorching conditions. This could result in organisms with robust, high-temperature resistant cellular structures composed of silicate minerals. The cellular membranes of silicon-based life forms might be composed of silicate-based materials, which are much more heat-resistant compared to carbon-based lipids found in Earth life. These membranes would need to be durable yet flexible enough to allow for selective permeability, critical for nutrient absorption and waste excretion. On Earth, certain microorganisms form silica shells. Similarly, silicon-based life might have silicate exoskeletons providing structural support and protection against environmental stresses. In cooler, more inert environments, such as the icy moons of the outer planets, silicon-based organisms could utilize the abundant silicon-oxygen compounds, like silicas and silicates, within the ice and rocky substrates. These life forms might resemble crystalline or glass-like structures, incorporating the surrounding materials into their biology. Their metabolism might involve breaking down silicates to extract energy, a process that would be far slower compared to the metabolic rates seen in carbon-based life on Earth. Silicon-based metabolic pathways could differ significantly. Given silicon's strong affinity for oxygen, silicon-based life might perform respiration through the oxidation of silicon compounds, producing silicon dioxide as a byproduct, a striking contrast to the carbon dioxide produced by carbon-based organisms. Such biochemical processes would necessitate a fundamentally different set of enzymes and catalytic molecules adapted to the stability and reactivity peculiar to silicon chemistry. The appearance of silicon-based life forms could range from rigid, rock-like organisms to flexible, amorphous structures. Their physical form would depend greatly on their specific environmental niches. In highly dynamic environments, they might evolve mobility mechanisms analogous to molten flow or the slow movement of tectonic plates, continuously adapting their form and function to the prevailing conditions. Exploring the concept of silicon-based life forces us to broaden our understanding of what life can be, challenging our carbon-centric view and emphasizing the adaptability and diversity that life might exhibit in the universe's myriad environments. Life in the upper atmosphere of gas giants such as Jupiter or Saturn would have to adapt to an extraordinarily challenging environment. Despite the setbacks, theorists suggest that certain niches within these massive planets might host life forms that defy our Earth-centric expectations. The upper atmospheres of gas giants are rich in hydrogen, helium, methane, ammonia, and other compounds, existing in a state akin to a chemically active soup. Life forms might exploit these available chemicals for metabolic processes. For instance, they could perform chemosynthesis, converting atmospheric elements into usable energy, much as certain Earth microbes do in extreme environments like deep-sea hydrothermal vents. Floating organisms, broadly dubbed aerial plankton, might occupy these layers by developing unique adaptations to remain buoyant amid thick gaseous atmospheres. They could possess gas-filled sacs or other buoyant structures, similar to helium balloons, allowing them to maintain a stable altitude within the relatively stable, more temperate upper regions, away from the intense pressures and lethal temperatures deeper down. Radiation is another considerable challenge, given that gas giants are subjected to intense magnetic fields and cosmic rays. Life forms might develop protective outer layers or pigmentation to shield them from harmful radiation. Additionally, they might have advanced repair mechanisms to fix DNA or other critical molecules damaged by radiation, similar to extremophiles on Earth. Another crucial consideration is nutrient acquisition and energy conversion. These life forms might have intricate systems to capture and metabolize trace organic molecules and gases. Imagine organisms that could stretch into long, filament-like structures to increase their surface area, absorbing more of the sparse nutrients available. They might also evolve highly efficient biochemical pathways to get the maximum energy from minimal input, relying on sophisticated forms of chemotrophy or other energy acquisition methods. Life in such unstable environments may also need to be highly adaptable, equipped to endure fluctuating temperatures, gas compositions, and weather conditions, similar to how some Earth bacteria can enter a state of dormancy during unfavorable conditions and resume activity when the environment becomes conducive again. Exploring the possibility of aerial life in gas giants pushes our understanding of life's limits and adaptability. While it remains speculative, it encourages us to expand our horizons, recognizing that life might find a way even in the most seemingly inhospitable locations, adapting its form and function to survive amid the gas giant's swirling clouds. Life in binary star systems, where two stars orbit a common center, presents an intriguing puzzle for scientists due to the complex and dynamic nature of their habitable zones. Habitable zones, or the Goldilocks zones, are regions around stars where conditions might be just right for liquid water to exist, a key ingredient for life as we know it. In a binary system, the gravitational influences and varying radiation from two stars can create a complicated, fluctuating habitable zone. For a planet to sustain stable conditions suitable for life, it would need to orbit in a stable region where the combined gravitational pull of both stars would not disrupt its orbit significantly. There are generally three scenarios for such stable orbits: close binary systems, where planets orbit both stars at a distance; wide binary systems, where planets orbit one star with the other star being far away; and intermediate systems, where planets have more complex orbital paths. For planets around close binary systems, the habitable zone would be more stable if the planet orbits far enough away from both stars together, avoiding the complex gravitational interactions. Here, the merged influences of both stars could create a wider and possibly more stable habitable zone, albeit one subject to fluctuations in temperature and radiation levels as the stars move around each other in their orbits. In wide binary systems, planets orbit one of the stars while the other star exerts minimal direct impact due to its distance. However, the distant star can still affect the shape and extent of the primary star's habitable zone through gravitational pulls and periodic variations in received radiation. Periodic eclipses or close encounters with this distant star could lead to fluctuations in climate on the planet, impacting the potential for life but also possibly encouraging adaptability and resilience in any life forms. Planets in intermediate systems, where they have more intricate orbits interacting significantly with both stars, pose the most challenges. These systems can experience dramatic shifts in environmental conditions. Life here would need to be extremely adaptable, possibly evolving mechanisms to cope with periodic extremes in temperature, radiation, and even tidal forces. Advanced forms of photosynthesis or chemosynthesis, robust protective shells, and highly effective mechanisms for repairing radiation damage could be key evolutionary traits. Despite these challenges, binary systems could offer unique and rich grounds for life to evolve. The variability and complexity might drive diverse evolutionary paths, potentially leading to life forms with extraordinary adaptability and resilience. The presence of two suns could provide dynamic environmental conditions that foster biological diversity, from organisms that thrive in varying levels of light and UV radiation to those that exploit the gravitationally induced geothermal activity. Thus, while binary star systems present a host of challenges for sustaining life, they also offer unique opportunities. Their complex habitable zones could foster a diversity of ecosystems, pushing the boundaries of how we understand life can adapt and thrive in the universe. Life on rogue planets, those celestial bodies that drift through interstellar space untethered to any star, would face a host of unique challenges due to the absence of a nearby star's warmth and light. However, such environments might also provide unexpected niches where extremophiles could evolve and thrive. The primary challenge for life on a rogue planet would be the extreme cold, as the absence of a star means these planets are far from any external heat source. Surface temperatures would plummet to nearly absolute zero, making the surface an unlikely habitat for life. However, beneath the icy crusts of such planets, there could be subsurface oceans kept liquid by geothermal heat generated from the planet's core. Just as under Europa and Enceladus within our solar system, internal heat sources might come from residual heat from the planet's formation, radioactive decay, or even tidal forces if the planet has sufficient mass or internal friction. Life in these subsurface oceans would rely on chemosynthesis instead of photosynthesis, extracting energy from chemical reactions rather than sunlight. Microbial life could cluster around hydrothermal vents on the ocean floor, akin to what we see around Earth's deep-sea vents. These vents could spew minerals and heat, providing the necessary conditions for life to thrive in an otherwise frigid environment. Organisms might utilize energy from reactions involving sulfur, methane, or hydrogen, fostering complex ecosystems despite the perpetual dark. Adaptation to such environments would involve several intriguing biological innovations. Organisms might develop anti-freeze proteins or other chemical adaptations to prevent their cellular fluids from freezing. Their biology would likely be highly efficient, maximizing the limited energy available. Life forms might evolve slow metabolic rates to conserve energy, entering states of dormancy during periods of lower geothermal activity. The chemistry of life on rogue planets might also differ depending on the planet's composition and available elements. For instance, some might develop silicon-based biochemistry if silicon is more abundant than carbon, leading to life forms with silica-based structures rather than carbon-based ones. The thick ice layer above these oceans would provide protection from cosmic radiation, allowing life to exist relatively undisturbed despite the harsh conditions of interstellar space. The potential discovery of life on rogue planets would significantly expand our understanding of life's adaptability and the variety of environments where life could arise. Such findings would suggest that life is not an Earth-centric phenomenon, but rather a versatile and resilient process capable of thriving in the most unexpected and extreme conditions the universe has to offer. Life evolving under the extreme pressures found on super-Earth exoplanets, planets significantly larger than Earth but smaller than Neptune, would likely feature extraordinary adaptations to survive and thrive in such environments. These adaptations would have to address the crushing forces, potentially staggering temperatures, and unique chemical settings of these colossal worlds. Under extreme pressures, life's molecular machinery might differ considerably from what we observe on Earth. Cell membranes, essential for isolating and protecting the interior of living cells, would need to be exceptionally robust and flexible. One hypothetical adaptation could involve using different lipid compositions, making the membranes more resistant to crushing forces. These biomolecules might even be reinforced with stronger compounds, possibly including elements like silicon or other high-strength materials to maintain cellular integrity. Metabolic processes in such environments would also need to adapt. Enzymes, the proteins that drive biochemical reactions, often rely on a precise structure to function. Under high pressure, normal protein structures could be destabilized. Therefore, super-Earth life forms might evolve enzymes that are structurally more compact or use metal cofactors that enhance stability and functionality under pressure. Additionally, metabolic pathways could be tuned to operate efficiently at higher temperatures, given that super-Earths might have geothermal activity or higher overall temperature gradients due to their larger mass and insulating atmospheres. The energy sources available to potential organisms could also be unique. On Earth, life sources its energy from both sunlight and chemical reactions. For life under super-Earth conditions, particularly in vast oceanic environments, chemical energy might play a more dominant role. Hydrothermal vents or other geothermal sources could provide the heat and chemical gradients necessary to support diverse ecosystems, similar to those found in Earth's deep-sea vent communities. Here, sulfur, iron, and other mineral-based chemistries might offer the primary substrates for energy extraction. Structural adaptations would also be necessary. Life forms could exhibit thick, compact bodies to withstand pressure, similar to how animals adapted to deep ocean environments on Earth. This might manifest as organisms with dense, cartilaginous or bony frameworks that provide internal support. Alternatively, they might exhibit fluid-filled or semi-fluid structures that distribute pressure evenly, reducing the strain on any singular point. Shells or exoskeletons could be composed of high-pressure tolerant materials, allowing organisms to maintain shape and mobility in a high-pressure environment. Sensing and communication mechanisms would also likely adapt. Sound travels faster and more efficiently under high pressure, so auditory or vibrational communication might be more prevalent. Whether through echolocation-like systems or pressure-sensitive organs, organisms would likely evolve acute awareness of their high-pressure surroundings. Life on super-Earths could push the boundaries of what we consider biologically possible, showing extraordinary versatility and resilience. The exploration of these worlds, even through theoretical models, advances our understanding of life's potential diversity in the universe and challenges our perceptions of the environments where life can take root. Surviving on a planet orbiting a neutron star would necessitate some of the most extreme adaptations imaginable for any form of life. These neutron stars are incredibly dense remnants of supernova explosions, possessing powerful gravitational forces and intense radiation, including X-rays and gamma rays. Life in such an environment would need to evolve extraordinary mechanisms to withstand these challenges. One of the foremost challenges is the intense radiation emitted by neutron stars. Life forms on a neutron star planet would require highly sophisticated radiation shielding. They might possess thick, radiation-absorbing exteriors, potentially composed of heavy elements or even specialized organic compounds that can neutralize or deflect radiation. Alternatively, they might live underground or within deep oceans, where rock or water layers provide natural protection from the relentless radiation bombardment. Another critical factor is the extreme gravitational forces near a neutron star, which would influence the structure and physiology of organisms. These life forms would likely need to be robust and compact to withstand the gravitational stress. On Earth, organisms like tardigrades showcase impressive adaptability to extreme conditions, including high pressure and radiation. Similar multi-layered cellular structures could evolve in neutron star life, with additional reinforcement mechanisms to prevent cellular collapse under gravity's intense pull. Metabolic processes would also have to adapt dramatically. Life forms might derive energy from geothermal or chemical sources, given that the extreme radiation could make surface conditions inhospitable. Chemosynthesis, the process used by certain Earth microbes to extract energy from chemical reactions, might be more common. These life forms could utilize unique chemical gradients provided by the planet's geological processes, potentially relying on sulfur, iron, or even exotic compounds present in such extreme environments. Sensory and communication systems would also likely be highly specialized. Due to the high-energy radiation and gravitational influences, traditional sensory mechanisms like vision might be impractical or non-existent. Instead, life forms might evolve to sense electromagnetic fields, radiation levels, or sonic vibrations. These adaptations could enable them to navigate their environment, communicate, and find food. Furthermore, the intense magnetospheres often associated with neutron stars might influence the physiology of these organisms. They could evolve magnetoreceptive abilities, similar to how some Earth species detect magnetic fields for navigation. Additionally, bioluminescence might be a prevalent trait, providing a way to signal and communicate in an environment where traditional light might be scarce or too dangerous to use extensively. Finally, reproductive strategies would need to ensure the continuation of life despite extreme and fluctuating conditions. Organisms might develop highly resilient spores or cysts capable of withstanding the most adverse conditions, waiting for more stable periods for growth and reproduction. Rapid adaptation and robust genetic diversity would be crucial, allowing life forms to evolve quickly in response to environmental pressures. Ultimately, life adapting to the harsh conditions of neutron star planets would exemplify nature's remarkable resilience and adaptability. Such life forms would push the boundaries of biological possibilities, offering profound insights into the potential diversity of life throughout the cosmos. The possibility of life in the subsurface oceans of Pluto-like objects, also known as trans-Neptunian objects, sparks curiosity and expands our understanding of where life might thrive. Despite their frigid surface temperatures and distant location from the sun, these icy bodies could host environments beneath their crusts conducive to life. Subsurface oceans on Pluto-like objects would be insulated by thick layers of ice, preventing the water from freezing solid despite the extremely low temperatures on the surface. This phenomenon is driven by internal heat sources, such as radioactive decay of elements within the planet's core or residual heat from the object's formation. Tidal forces, generated by gravitational interactions with nearby objects, could also provide additional heat through friction, maintaining a liquid state in the subsurface oceans. Life in these hidden oceans would likely rely on chemosynthesis, a process where organisms derive energy from chemical reactions rather than sunlight. This mirrors the ecosystems found around hydrothermal vents in Earth's deep oceans, where microbes utilize minerals emitted by the vents for energy. In the subsurface oceans of Pluto-like objects, similar hydrothermal activity could occur. Geological processes on the seafloor might provide a rich chemical environment, with compounds like methane, ammonia, and sulfur serving as potential energy sources. Organisms in these extreme environments would need to possess unique biochemical adaptations to thrive. Their cellular structures would be optimized for functioning under high-pressure, low-temperature conditions. Antifreeze proteins or other molecular adaptations might be prevalent, preventing the integrity of cellular fluids in the cold. Their metabolic processes would be geared towards efficiency in nutrient-poor environments, with adaptations to maximize energy extraction from available resources. Given the darkness of these subsurface oceans, life forms might also develop sensory mechanisms that do not rely on light. Chemoreceptors to detect chemical gradients or mechanoreceptors to sense movement and vibrations would be essential for navigation and finding food. Bioluminescence might serve as a means for communication or attracting prey, with organisms using light-producing reactions to make themselves visible in pitch-black waters. The diversity of potential life forms might be extensive. Simple microbial life could form the foundational base of the ecosystem, with more complex multicellular organisms evolving over time. In such a chemically rich environment, life forms might evolve into unique shapes and behaviors, conditioned by the need to adapt to high-pressure, dark, and cold surroundings. Exploring these subsurface oceans would require innovative technology, such as ice-penetrating probes that can drill through the icy crust and deploy submersibles into the ocean beneath. By studying these environments, scientists could uncover new insights into the resilience and adaptability of life, stretching the boundaries of our understanding and opening up new possibilities in the search for extraterrestrial life. When galaxies collide, the impacts are both dramatic and intricate, fundamentally reshaping the structure and activity of the involved galaxies. Despite the violent imagery the word collision may evoke, it is important to note that stars within galaxies are so far apart that they rarely collide directly. Instead, the gravitational interactions are the main drivers of the phenomena observed during galactic collisions. As two galaxies approach each other, their mutual gravitational forces begin to tug at the star's gas and dust within them. This interaction can strip stars from their original orbits, creating tidal tails, streamers of stars and gas stretching out from the interacting galaxies. These spectacular structures are a visible testament to the gravitational forces at work. A critical consequence of galactic collisions is the triggering of star formation. When galaxies collide, their interstellar gas clouds can be compressed, leading to shock waves that trigger the collapse of gas clouds into new stars. This often results in starburst galaxies, where star formation rates are significantly higher than in quiescent, non-interacting galaxies. The new stars tend to be massive and bright, driving energetic phenomena such as supernovae, which, in turn, enrich the interstellar medium with heavier elements. However, the long-term effects of galactic collisions on star formation can be varied. In the initial stages, as starbursts ignite, the rate of star formation skyrockets. Over time, though, prolonged or multiple collisions and mergers can deplete the available gas, quenching star formation. The merging of the supermassive black holes at the centers of the colliding galaxies can also play a role. As these black holes grow and become active, they can generate powerful jets and winds that blow away or heat up the remaining gas, further suppressing subsequent star formation. Galactic collisions can also lead to the formation of new galaxy types, such as elliptical galaxies. Ellipticals are typically formed from the merger of spiral galaxies, with the resulting system displaying a smoother, more featureless appearance. These galaxies often lack the raw material for new stars, leading to a mostly older, redder population of stars compared to their progenitors. Overall, the collision and subsequent merging of galaxies is a transformative process that alters the dynamics, structure, and star formation activity of the involved galaxies. By studying these cosmic events, astronomers gain crucial insights into the life cycles of galaxies and the intricate dance of gravitational forces that shape the universe. Binary neutron star mergers are extraordinary cosmic events that play a crucial role in the production of heavy elements in the universe. When two neutron stars, the ultra-dense remnants of massive stars that have undergone supernova explosions, spiral towards each other and collide, they unleash a cataclysmic burst of energy and matter. The process begins with the intense gravitational interaction between the two neutron stars, causing them to orbit closer and closer over time. This in-spiraling emits gravitational waves, ripples in the fabric of space-time, that we can now detect with instruments like LIGO and Virgo. As the neutron stars merge, they create a violent explosion known as a kilonova, which is significantly brighter than a typical nova, although not as intense as a supernova. During the merger, the extreme conditions virtually unparalleled in the universe are achieved, including immense pressures and temperatures. These conditions provide a fertile environment for the rapid neutron capture process, or R process. In the R process, atomic nuclei capture neutrons extremely quickly, allowing them to build up to heavy neutron-rich isotopes before they can decay. This rapid succession of neutron captures helps form elements much heavier than iron. Following the merger, the merged object can either become a more massive neutron star or collapse into a black hole depending on its mass. Regardless of the outcome, the merger ejects an enormous amount of neutron-rich material into space. As this material expands and cools, it undergoes radioactive decay, transforming the neutron-rich isotopes into stable heavy elements like gold, platinum, uranium, and neodymium. This entire nucleosynthesis process can produce substantial amounts of these heavy elements, seeding them into the surrounding interstellar medium. Observations of kilonova events have provided direct evidence of this heavy element production. For example, The detection of the gravitational wave event GW170817 and its electromagnetic counterpart confirmed that neutron star mergers significantly contribute to the cosmic abundance of heavy elements. The light curves and spectra from such events match the predictions of our process nucleosynthesis, revealing the synthesis of new elements in real time. Binary neutron star mergers are cosmic forges where the universe's heaviest elements are created. This process enriches the interstellar medium with these elements, which can later be incorporated into new stars, planets, and even the material that makes up life, showing the interconnectedness of cosmic events and our own existence. The merger of supermassive black holes has profound consequences for their host galaxies, impacting their structure, dynamics, and even their capacity to form new stars. These titanic events occur when galaxies collide and their central black holes, each millions to billions of times the mass of the Sun, eventually coalesce into an even larger supermassive black hole. One immediate consequence of supermassive black hole mergers is the disruption of stellar and gaseous material in the galaxy's cores. As the black holes approach each other, they exert powerful gravitational forces that can cause stars and gas clouds to be ejected from the galactic center or to settle into new orbits. This process can create a more relaxed, spheroidal distribution of stars, transforming the galaxy's core. The gravitational interactions may also trigger episodes of intense star formation as gas clouds are compressed, or conversely, star formation may be quenched if the gas is expelled from the central regions. Another significant effect is the emission of gravitational waves during the merger process. This radiation is so powerful that it carries away some of the merged black hole system's energy and momentum, causing the merged supermassive black hole to recoil, a phenomenon known as gravitational wave recoil or kick. Depending on the magnitude of this recoil, the newly formed supermassive black hole may be displaced from the center of the galaxy or, in extreme cases, ejected entirely. If displaced but retained within the galaxy, the wandering black hole can continue to influence the dynamics and evolution of the galactic nucleus. The activity associated with merging supermassive black holes can also ignite what is known as an active galactic nucleus. If ample gas and dust feed the accretion disks surrounding the black holes during and after the merger, the intense gravitational forces can heat up the material to extreme temperatures, causing it to emit powerful radiation across the electromagnetic spectrum. This AGN phase can be observable as a quasar, blazar, or radio galaxy, which can outshine the rest of the host galaxy and affect the ionization state of the interstellar medium. Moreover, the jets and winds produced by the AGN can have a profound feedback effect on the host galaxy. These outflows can heat the interstellar gas or even expel it from the galaxy's core, inhibiting subsequent star formation by removing the raw material needed for making new stars. This feedback mechanism can regulate the growth of the galaxy, maintaining a balance between the central black hole's growth and the development of the stellar component of the galaxy. Supermassive black hole mergers do not merely affect the immediate surroundings, their repercussions can reshape the entire host galaxy. From altering the galactic core and triggering or quenching star formation to generating observable AGN activity and powerful gravitational waves, these colossal events highlight the dynamic and interconnected nature of cosmic evolution. Planetary collisions play a significant and multifaceted role in shaping the formation and evolution of solar systems. During the early stages of a solar system's development, collisions among protoplanets, planetesimals, and other celestial bodies are frequent and instrumental in defining the final architecture of the system. In the protoplanetary disk of gas and dust surrounding a young star, small particles begin to clump together through electrostatic forces and gravity, forming larger bodies known as planetesimals. These planetesimals collide and merge, growing into protoplanets over time. These collisions are crucial for building larger planetary bodies, a process known as accretion. Through countless impacts, material aggregates to form the cores of what will become planets. Significantly, these early frequent collisions also contribute to the diversity of planet sizes and compositions observed in mature solar systems. For instance, the giant impact hypothesis for the Moon's formation suggests that a Mars-sized protoplanet collided with the early Earth. This catastrophic event not only led to the formation of the Moon, but also significantly influenced Earth's own evolution, delivering additional material that helped shape its composition and contributing to its axial tilt, which affects the planet's climate and seasons. Collisions in the later stages of planetary formation can also redistribute material within the solar system. Massive impacts can strip planets of their atmospheres, redistribute volatiles like water, and even lead to the exchange of material between planets. This exchange can contribute to planetary diversity. For example, water and organic molecules may be delivered to terrestrial planets through impacts with icy bodies or comets, potentially playing a role in the emergence of life. The gravitational interactions and collisions ultimately help clear the remaining debris in the solar system, leading to a more stable configuration of planetary orbits. These late cleanup processes are essential for reducing the number of potentially catastrophic impacts on the fully formed planets, allowing for more stable environments where life can potentially evolve. The era of heavy bombardment in our own solar system about 4 billion years ago is thought to have played a role in shaping the surfaces of the terrestrial planets and influencing their geological histories. In addition, planetary collisions can contribute to the formation of secondary features such as rings and moons. The debris from collisions can coalesce into ring systems or be captured as moons, adding to the complexity and beauty of planetary systems. Therefore, planetary collisions are not merely destructive phenomena. They are fundamental to the creation and evolution of solar systems. By driving the growth of planets, altering their compositions, shaping their atmospheres, and influencing their orbits, these cosmic impacts contribute to the rich tapestry of planetary systems we observe in the universe today. When a star collides with a black hole, the event is both catastrophic and dramatically transformative. The outcomes depend significantly on the mass of the black hole and the characteristics of the star. These encounters involve intense gravitational forces, extreme energy releases, and fascinating astrophysical phenomena. As a star approaches a black hole, tidal forces exerted by the black hole's immense gravity begin to distort the star. This tidal stretching can lead to a phenomenon known as a tidal disruption event if the star gets close enough to be torn apart. The point at which this occurs is called the tidal radius. When a star is within this tidal radius, the differential gravitational pull between the near and far sides of the star can be so extreme that it overcomes the star's internal gravity, resulting in the star being stretched and ultimately torn into streams of gas. These stellar remnants then spiral inward towards the black hole, forming an accretion disk around it. As the gas in this disk accelerates and heats up due to friction and gravitational forces, it emits intense radiation, often producing a bright flare visible across vast distances. This dramatic flaring can shine in multiple wavelengths, from ultraviolet to X-rays and even gamma rays. Such a flare is a telltale sign of a TDE and provides astronomers with clues about the conditions near the black hole and the nature of the consumed star. The process of the star being drawn into the black hole can take from weeks to months, during which the black hole ingests the stellar debris. In the case of smaller black holes, known as stellar mass black holes, the effects can be equally cataclysmic but more localized. If a star were to collide with a binary stellar mass black hole system, the outcomes could include gravitational wave emission detectable by observatories like LIGO and Virgo, as well as disruptions in the surviving star's orbit, potentially ejecting it at high velocities. If the black hole is significantly more massive, such as a supermassive black hole found at the centers of galaxies, the tidal disruption can lead to more spectacular and observable phenomena. The energy released in such events can impact the surrounding galaxy, influencing star formation rates and heating interstellar gas. Additionally, relativistic jets may form perpendicular to the accretion disk, propelling particles at nearly the speed of light, and contributing to high-energy astrophysical jets observable across the universe. These dramatic collisions also provide valuable data for scientists studying the physics of black holes and the extreme conditions in their vicinity. Observations of TDEs and the resulting emissions offer insights into the rates at which such events occur, the properties of black holes, and the dynamics of stars in galactic centers. Ultimately, the collision between a star and a black hole exemplifies some of the universe's most extreme and energetic processes, highlighting the power and complexity of gravitational interactions in shaping cosmic phenomena. Galaxy cluster collisions, some of the most titanic events in the universe, have profound effects on the distribution of dark matter within and around the involved clusters. These colossal mergers provide valuable insights into the elusive nature of dark matter, which constitutes about 25% of the universe's total mass, yet interacts primarily through gravity, without emitting, absorbing, or reflecting light. During a collision between two galaxy clusters, the galaxies themselves often pass by each other relatively undisturbed due to the vast spaces between them. However, the hot gas within the clusters, which makes up the bulk of their normal matter and is visible in X-rays, experiences significant friction and slows down, eventually forming a single, more concentrated cloud of hot gas at the center of the collisions. In contrast to the baryonic matter, dark matter, which is thought not to interact through electromagnetic forces, behaves differently during these colossal encounters. One of the most striking pieces of evidence for the behavior of dark matter in cluster collisions comes from observations of systems like the bullet cluster. In such systems, the dark matter appears to pass through the collision relatively unimpeded, unlike the gas. This creates a separation between the dark matter and the normal matter. Gravitational lensing, the bending of light from background galaxies due to the cluster's gravitational field, is used to map the distribution of dark matter. In the aftermath of a collision, these maps show dark matter concentrations behind the hot gas cloud, indicating that dark matter does not slow down or stick together in the way that baryonic matter does. This separation indicates that dark matter interacts very weakly, if at all, with itself or with normal matter beyond gravitational interactions. Furthermore, the difference in behavior between dark matter and baryonic matter during these collisions allows astronomers to study the properties of dark matter more precisely. For instance, by measuring the amount of separation between dark matter and hot gas, researchers can set limits on the self-interaction cross-section of dark matter particles, providing clues about the fundamental nature of these elusive particles. Galaxy cluster collisions also contribute to the overall distribution of dark matter on larger cosmic scales. As clusters merge and form superclusters, they create vast cosmic structures, enhancing our understanding of the large-scale architecture of the universe. These observations help refine cosmological models and simulations, shedding light on how dark matter drives the formation and evolution of cosmic structures. Galaxy cluster collisions serve as natural laboratories for exploring dark matter's properties and behaviors. By studying these events and their aftermath, scientists can glean crucial information about the fundamental forces governing the universe and the mysterious nature of dark matter itself. When white dwarfs in binary systems merge, the consequences are dramatic and far-reaching, leading to a range of astrophysical phenomena. White dwarfs are the remnants of medium-sized stars that have burned out their nuclear fuel and collapsed into incredibly dense, Earth-sized objects. When two such stars come together, their merger can result in explosive events, the formation of new compact objects, and significant contributions to our understanding of cosmic evolution. One of the most notable outcomes of a white dwarf merger is a type Ia supernova. This occurs when the combined mass of the merging white dwarfs exceeds the Chandrasekhar limit, roughly 1.5 times the mass of the Sun. The merger initiates runaway nuclear fusion, producing a stupendous amount of energy that leads to a thermonuclear explosion. The resulting type Ia supernova is incredibly luminous, outshining entire galaxies for weeks or months and serving as a critical standard candle for measuring cosmic distances. These supernovae help astronomers determine the expansion rate of the universe and probe the nature of dark energy. In cases where the combined mass of the merging white dwarfs does not exceed the Chandrasekhar limit, other interesting outcomes are possible. The merger can produce a more massive white dwarf, surrounded by a disk of leftover material. This massive white dwarf is hotter and may spin more rapidly than the two progenitors. Over time, it can cool and settle into a stable, high-mass configuration. This outcome enriches our understanding of the diversity of white dwarf populations and their properties in binary systems. Another scenario involves the possibility of forming a neutron star. If the merger leads to enough pressure and temperature, the resulting object can collapse into a neutron star, a more compact and dense remnant than a white dwarf. This process introduces a different kind of compact object, contributing to the inventory of neutron stars in the universe and influencing their distribution and evolution. White dwarf mergers also contribute to the production of heavy elements via nuclear synthesis. The intense conditions during the merger can lead to the creation of elements heavier than iron, enriching the interstellar medium with these building blocks. This process plays a critical role in the chemical evolution of galaxies, providing the raw materials for future generations of stars and planets. Furthermore, these mergers can lead to the emission of gravitational waves. As the white dwarfs spiral towards each other before merging, they produce ripples in space-time. These waves can be detected by gravitational wave observatories, contributing to our understanding of such phenomena and enhancing our ability to probe the universe through this new observational window. Overall, white dwarf mergers in binary systems are transformative astrophysical events that significantly impact our understanding of stellar evolution, chemical enrichment, gravitational wave astronomy, and the cosmic distance scale. Each merger outcome helps paint a more comprehensive picture of the dynamic and complex processes that shape our universe. Stellar collisions in globular clusters, which are densely packed collections of stars orbiting the core of a galaxy, play a significant role in the evolution of these ancient stellar systems. Given the high stellar densities within globular clusters, the chances of stars interacting and even colliding are much higher than in less densely populated regions of a galaxy. These interactions have profound implications for the properties and dynamics of the cluster. One of the immediate consequences of stellar collisions in globular clusters is the formation of exotic objects. For example, when two stars collide, they can merge to form a single, more massive star. These collision products may appear hotter and bluer than the other stars in the cluster, even if they are quite old. Known as blue stragglers, these stars stand out in globular clusters because they appear to be younger than their peers. Blue stragglers provide crucial insights into stellar evolution and dynamics within the cluster. Another outcome of stellar collisions is the formation of binary systems, where two stars orbit a common center of mass. In the crowded environment of a globular cluster, frequent close encounters can lead to the exchange of stellar companions, formation of new binaries, or tightening of existing binaries. These interactions can catalyze the evolution of the stars involved, as binary interactions often lead to mass transfer, the stripping of outer layers, and the initiation of new nuclear burning processes. These binaries can drive a variety of phenomena, including the formation of X-ray binaries and millisecond pulsars. Collisions and close encounters also significantly affect the dynamical evolution of the globular cluster itself. Energy exchange during these interactions, where kinetic energy is redistributed among the stars, gradually leads to mass segregation. In this process, more massive stars move towards the cluster's core, while less massive stars migrate to the outskirts. This segregation can lead to core collapse, wherein the core of the cluster becomes denser over time, further increasing the rate of stellar interactions and collisions. Gravitational interactions and collisions also contribute to the long-term stability and lifespan of globular clusters. These interactions help to dynamically heat the cluster, counteracting the tendency for the system to collapse gravitationally. By redistributing energy among the stars, these encounters can prolong the cluster's existence and prevent it from disintegrating. Moreover, stellar collisions and interactions may expel some stars from the cluster altogether. High-velocity stars can be ejected from the cluster during close encounters, contributing to the population of runaway stars in the galaxy. This loss of stars can slowly whittle away the mass of the globular cluster over billions of years, continually reshaping its structure. Ultimately, stellar collisions within globular clusters are a crucial aspect of their complex and dynamic evolution. These interactions create a diverse array of stellar phenomena, influence the overall dynamical state of the cluster, and provide a wealth of information about stellar dynamics and evolution in some of the oldest systems in the universe. By studying these dense stellar environments, astronomers gain deep insights into the fundamental processes that govern star formation, interaction, and life cycle. When rogue planets, which are planets drifting through space unbound to any star, collide or interact with established planetary systems, a variety of consequential events can unfold, fundamentally altering the dynamics and structure of the affected systems. These interlopers, moving through interstellar space, can enter planetary systems through gravitational interactions or sheer chance, creating a range of potential outcomes. One of the most dramatic possibilities is a direct collision between the rogue planet and an existing planet in the system. Such an impact would generate immense forces, releasing a substantial amount of kinetic energy and leading to catastrophic outcomes. The collision could obliterate smaller planets, leaving behind a debris field of rock and dust. This material could form a temporary ring around the affected star, or accrete to form new moons or smaller planetary bodies over time. Additionally, the impact's energy would generate significant heat, melting and reshaping any surviving planetary fragments. Even without a direct collision, the gravitational influence of a rogue planet passing near an established planetary system can wreak havoc on the orbital dynamics of the system. A rogue planet's gravity can perturb the orbits of planets, asteroids, and comets, potentially causing them to shift into more eccentric or inclined paths. These disturbances can lead to increased chances of collisions among the system's existing celestial bodies, triggering a chain reaction of impacts and further dynamical chaos. Moreover, the gravitational force of a rogue planet can destabilize the orbits of smaller bodies in the system, such as comets and asteroids. This perturbation might send these objects hurtling towards the inner planets, increasing the frequency of impact events and possibly leading to significant geological and atmospheric changes on those planets. For example, an increase in asteroid impacts could contribute to surface erosion, atmospheric changes, or even mass extinction events if life were present. In systems with multiple planets, a rogue planet's intrusion could disrupt the delicate gravitational balance, potentially resulting in orbital resonance changes. Planets might be ejected from their orbits, either being sent into deep space as new rogue planets themselves, or pushed into highly elliptical orbits that drastically change their environmental conditions. In some cases, planets could be thrown inward or outward, closer to or further from the star, leading to significant changes in temperature and potential habitability. While these scenarios may sound catastrophic, it is also possible that a rogue planet could be captured by the host star's gravity and become a new member of the established planetary system. Such a capture would depend on the rogue planet's velocity, trajectory, and the gravitational field of the host star. Once captured, the rogue planet could settle into a stable orbit, enriching the system with another planet. Its presence could lead to long-term dynamic changes, but without the immediate destructive effects of a collision or close encounter. Thus, when rogue planets interact with established planetary systems, the outcomes can range from complete destruction of existing bodies to significant yet non-catastrophic dynamical changes, and even to the potential addition of a new planet to the system. These interactions highlight the complex and ever-evolving nature of planetary systems and underscore the chaotic processes that can shape their formation and evolution across the cosmos. By studying these interactions, astronomers gain valuable insights into the factors that influence planetary dynamics and the resilience or fragility of planetary systems. Collisions between cosmic rays and particles in the interstellar medium are high-energy events that can lead to the creation of new elements through a process known as spallation. Cosmic rays are highly energetic particles, primarily protons, but also including heavy ions, that travel through space at nearly the speed of light. When these cosmic rays collide with nuclei of atoms in the interstellar medium, they can result in the fragmentation of those nuclei, producing new, lighter elements. The process begins when a high-energy cosmic ray particle, such as a proton or a heavier ion like a carbon or iron nucleus, collides with the nucleus of an atom in the interstellar medium, which might be composed of hydrogen, helium, or heavier elements. The enormous energy involved in this collision is sufficient to overcome the nuclear binding energy, causing the target nucleus to break apart or spall, generating lighter nuclei and a shower of subatomic particles, such as neutrons and protons. Through spallation, heavier elements like carbon, nitrogen, and oxygen in the interstellar medium can be fragmented into lighter nuclei, producing elements like lithium, beryllium, and boron. These lighter elements are relatively rare in the universe compared to heavier elements because they are generally not produced in significant quantities by standard stellar nucleosynthesis processes within stars. Therefore, cosmic ray spallation is a crucial mechanism for the synthesis of these rare elements. For instance, lithium-6 and lithium-7 can be produced when cosmic rays collide with carbon or oxygen nuclei, causing them to fragment. Similarly, beryllium-10 and boron-11 can be produced from the spallation of nitrogen, carbon, or oxygen nuclei. The newly created elements might be dispersed into the interstellar medium, where they can eventually become part of new stars, planets, and other celestial bodies. Furthermore, cosmic ray collisions contribute to the enrichment of the interstellar medium with a diverse array of isotopes and elements. This ongoing process influences the chemical evolution of galaxies as the newly formed elements and isotopes become incorporated into future generations of stars and planetary systems. By understanding the role of cosmic ray spallation, astronomers can better grasp the complexities of element formation and the distribution of elements in the universe. In addition, these interactions between cosmic rays and the interstellar medium can be observed and studied through the detection of gamma rays and other secondary particles produced in the collisions. These observations help scientists understand the origin, composition, and energy of cosmic rays, as well as the properties of the interstellar medium itself. Ultimately, cosmic ray spallation is a vital process that plays a key role in the chemical enrichment of the universe, creating some of the lighter elements that might not otherwise be abundant and aiding in the overall complexity and diversity of cosmic matter. The ultimate fate of black holes in an expanding universe is a topic of considerable interest and speculation among cosmologists and theoretical physicists. While black holes are often regarded as the most stable and enduring objects in the universe, they are not impervious to change over the grandest timescales. Several factors influence their long-term destiny, particularly in the context of an ever-expanding universe dominated by dark energy. One of the primary processes affecting black holes over unimaginable timescales is Hawking radiation, a theoretical prediction made by physicist Stephen Hawking. According to this theory, black holes can emit radiation due to quantum effects near their event horizons. This radiation results in the gradual loss of mass and energy from the black hole. Although this process is extremely slow for massive black holes, it implies that black holes are not entirely eternal entities. For a black hole with the mass of our Sun, the evaporation timescale due to Hawking radiation is far longer than the current age of the universe. However, given enough time, on the order of many trillions of years, even the most massive black holes will gradually shed their mass via Hawking radiation, ultimately leading to their complete evaporation. As they evaporate, they will become smaller and hotter, emitting increasing amounts of radiation until they eventually vanish in a final burst of energy. In an expanding universe, the impact of dark energy adds another layer of complexity to the fate of black holes. Dark energy, which drives the accelerating expansion of the universe, will continue to dominate the large-scale structure of the cosmos. As the universe expands at an accelerating rate, galaxies will move further apart, and the observable universe will become increasingly isolated. Individual black holes will become increasingly cut off from other matter and energy sources, potentially accelerating their isolation and individual evaporation processes. When considering the far future beyond the lifespan of stars and even black holes, we enter what is known as the dark era of the universe. During this epoch, nearly all matter will have either decayed or merged, leaving behind fundamental particles and black holes shrinking via Hawking radiation. The ultimate end state of the universe will be shaped by the fate of these remaining black holes. Over even longer timescales, as black holes completely evaporate, the universe will be left with a thin soup of fundamental particles and low-energy photons. This era represents a state of maximal entropy, often referred to as the heat death of the universe, where thermodynamic equilibrium is reached, and no further work or organized structure can exist. Thus, while black holes are among the most enduring structures in the universe, they are not immune to the inexorable march of cosmic time. Through processes like Hawking radiation and the influence of dark energy, black holes will gradually lose their mass and eventually disappear, contributing to the continuing evolution and eventual fate of the universe. This perspective provides a profound view of the ultimate destiny of cosmic structures and the intricate forces shaping their long-term evolution. The accelerating expansion of the universe, driven by dark energy, will have profound implications for galaxy formation and the large-scale structure of the cosmos in the far future. As the expansion accelerates, the distances between galaxies, galaxy clusters, and other large-scale structures increase at an ever-growing rate. This process will fundamentally alter the dynamics of the universe and the potential for new galaxy formation. One major consequence of the accelerating expansion is the increasing isolation of galaxies. As space expands, galaxies will recede from one another more rapidly, leading to vast, empty gaps between them. Over billions of years, this expansion will cause galaxies to move beyond the observable horizon of other galaxies, essentially disappearing from each other's visibility due to the finite speed of light. This isolation means that galaxies will no longer interact or merge, processes that are crucial for the formation of new galaxies. In the universe's current epoch, galaxy mergers and interactions play a significant role in shaping galaxies and stimulating star formation. These interactions lead to the accumulation of gas that can collapse to form new stars and potentially new smaller galaxies. As the universe continues to expand, the rate of these interactions will decrease markedly. Eventually, galaxies within groups and clusters will drift apart to such an extent that new galaxy formation via mergers will become extremely rare, if not entirely non-existent. Furthermore, as galaxies become isolated, they will exhaust their internal supplies of gas through star formation over time. Without fresh infall of gas from the intergalactic medium, because the distances will become too vast for material to diffuse back into galaxies, there will be little new raw material available to form new stars or sustain galaxy formation. Existing stars will age and eventually die, leaving behind stellar remnants like white dwarfs, neutron stars, and black holes. In an accelerating universe, the intergalactic medium itself will become increasingly sparse and ionized. Newly formed galaxies require substantial clouds of gas to collapse under gravity. However, with the accelerating expansion, these gas clouds are less likely to come together to form new galaxies, as they will be increasingly stretched and dispersed over time. The expansion also means that the growth of large-scale structures such as galaxy filaments and clusters will eventually slow down and stop. Gravity will no longer be sufficient to counteract the expansion on these scales, leading to a universe where existing structures remain relatively static in their current form, but no new large-scale formations can occur. Gradually, the universe will enter a state where galaxy formation ceases altogether, and the cosmos is left with widely separated galaxies, each containing aging stellar populations. The accelerating expansion thus leads to a cosmic freeze-out, where the dynamic processes that drive galaxy formation and evolution slowly wind down. The accelerating expansion of the universe will drastically reduce and eventually halt the formation of new galaxies. As galaxies become increasingly isolated, star formation within them will peter out, leading to a quiet, aging universe. This far-future cosmos will be characterized by dark, vast expanses with dwindling stellar processes, a stark contrast to the vibrant, interconnected universe we observe today. The gradual burning out of stars will profoundly impact the potential for life in the universe over cosmic timescales. As stars age and eventually die, the environments that currently support life will undergo dramatic transformations, leading to significant evolutionary pressures and potential migrations for any existing life forms. Initially, life as we understand it is likely tied to the life cycles of stars. Stars produce the energy necessary to sustain life through processes like photosynthesis and maintain habitable conditions on surrounding planets. As main-sequence stars like our Sun exhaust their nuclear fuel, they evolve into red giants, expanding enormously and dramatically changing their surrounding environments. During this phase, any nearby planets, particularly those in the habitable zone, may be engulfed or rendered uninhabitable due to intense heat and radiation. Following the red giant phase, stars shed their outer layers and leave behind remnants such as white dwarfs. While white dwarfs are no longer sites of nuclear fusion, they remain hot for billions of years, gradually cooling over time. In theory, planets orbiting at the right distance from these cooling white dwarfs could stay habitable for extended periods. However, maintaining life in such systems would require unique adaptations to deal with diminishing energy output over time. For more massive stars, the end stages involve supernova explosions, which can obliterate nearby planets but also distribute heavy elements necessary for planet formation and life into the interstellar medium. The remnants, neutron stars and black holes create environments hostile to conventional life due to intense gravity and radiation conditions, although speculative forms of life adept at harnessing exotic forms of energy could be imagined. Once the era of active star formation ends and existing stars fade away, the universe will transition to the so-called degenerate era, dominated by stellar remnants like white dwarfs, neutron stars, and black holes. During this period, traditional life forms relying on starlight would likely face extinction unless they evolve or find alternative energy sources. Life might shift to dependence on geothermal or other residual energy sources from planetary interiors, or even harness energy from black hole accretion disks or Hawking radiation. Life forms may also develop advanced technological means to survive, extracting energy from the surrounding environment with exceptional efficiency. Highly developed civilizations could build artificial habitats orbiting remaining energy sources or generate energy through advanced technological processes. As the universe drifts further into darkness, leading to the black hole era, where stellar remnants themselves evaporate via Hawking radiation, the prospects for life dim further. At this stage, free energy will be exceedingly sparse, requiring life to adapt to a virtually zero-energy environment. Eventually, life in its current form might become unsustainable, and any remaining entities would need to be highly efficient at conserving and utilizing energy. The ultimate fate of life in the universe is intertwined with the decay of cosmic structures anticipated in the far future epochs. The The gradual burning out of stars will necessitate incredible adaptability or technological advancement for life to persist. While conventional life forms may vanish, the potential for highly evolved or artificial forms of life to endure remains an intriguing and open question, illustrating the resilience and ingenuity of life in the face of cosmic impermanence. The nature of dark energy, the mysterious force driving the accelerated expansion of the universe, will profoundly influence the long-term evolution of the cosmos. Depending on its properties, dark energy could lead to various potential cosmic fates, each with unique implications. One widely accepted model is the cosmological constant, where dark energy density remains constant over time. In this scenario, the accelerated expansion will persist indefinitely. As time progresses, galaxies will move further away from each other, making the universe increasingly more expansive and isolated. This perpetual expansion will eventually push galaxies beyond the observable horizon of each other, effectively isolating local groups or clusters of galaxies. Star formation will decline as galaxies exhaust their gas reserves, leading to a cosmic dark age dominated by stellar remnants such as white dwarfs, neutron stars, and black holes. Over trillions of years, even these remnants will evaporate or decay, leaving behind a cold, dark, and dilute universe. Another possibility involves a dynamic form of dark energy, such as quintessence, where the dark energy density could change over time. Depending on its behavior, quintessence could either decelerate or accelerate the universe's expansion differently than a cosmological constant. If the dark energy density decreases over time, gravitationally bound systems could eventually dominate again, reversing the accelerated expansion and potentially leading to a gradual, slow contraction. Conversely, if the dark energy density increases, the universe could face outcomes even more extreme than endless expansion. One speculated extreme outcome is the Big Rip. In this scenario, if the dark energy density increases rapidly enough, it will overpower all other forces in the universe. The expansion rate would accelerate so dramatically that first galaxy clusters and then individual galaxies would be torn apart. Eventually, stars, planets, and even atomic structures could be ripped apart as the scale factor of the universe grows toward infinity within a finite time. The Big Rip would culminate in a catastrophic end where all structures disintegrate. Yet another possible fate influenced by dark energy is the Big Freeze, or heat death. This is associated with an ever-accelerating expansion where the universe asymptotically approaches a state of maximum entropy. In this scenario, the expansion continues to spread matter and energy thinly across an ever larger volume, leading to an increasingly uniform, cold, and dark universe. Eventually, all thermodynamic processes cease, and the universe reaches thermal equilibrium, where no work or organized activity can occur. There is also the speculative possibility of a big crunch, where the expansion could reverse, causing the universe to collapse back into a highly dense and hot state. This would require a change in the nature of dark energy, such as transforming it into a form that acts as attractive rather than repulsive force. While current evidence strongly supports continued acceleration, we cannot entirely rule out this scenario with our current understanding. Each of these potential futures reflects the profound impact that the unknown properties of dark energy can have on the cosmos. The ultimate fate of the universe, intricately linked with the nature of dark energy, remains one of the most fascinating and fundamental questions in cosmology. Future observations and theoretical advancements will continue to probe the characteristics of dark energy, gradually unveiling the long-term destiny of the cosmos. The possibility of a Big Rip scenario hinges on the properties of dark energy, particularly its equation of state, which describes the relationship between its pressure and density. In the Big Rip scenario, space itself would be torn apart due to an ever-increasing rate of expansion driven by a hypothetical form of dark energy with a particular characteristic. Its equation of state parameter, the ratio of dark energy pressure to its energy density, is less than -1. This kind of dark energy is sometimes referred to as phantom energy. If W is indeed less than -1, dark energy's repulsive effect would not only accelerate the expansion of the universe, but would do so at an increasing rate over time. This would lead to a situation where the repulsive force overwhelms all forms of gravitational and cohesive forces, resulting in the eventual tearing apart of all structures in the universe, including galaxies, stars, planets, and even atomic and subatomic particles. In the Big Rip scenario, if phantom energy drives the expansion, the universe's fate unfolds dramatically. First, galaxy clusters would begin to drift apart as the influence of dark energy strengthens. Galaxies that are currently bound together by gravity would eventually be overcome by this force and start receding from one another. As the expansion accelerates, individual galaxies would also come under the influence of dark energy. The gravitational forces holding stars together within galaxies would be overwhelmed, causing the stars to move apart and effectively dissolving the galaxies. Moving to smaller scales, planetary systems around stars would start to disintegrate. As the expansion rate increases further, planets would be pulled away from their orbits. In the final stages of the Big Rip, the repulsive force would become so intense that molecular bonds holding together atoms and even subatomic particles like protons and neutrons would be ripped apart. The fabric of space-time itself would be stretched to the breaking point, leading to a final catastrophic disintegration everywhere in the universe at a specific future time. The Big Rip scenario remains speculative and is dependent on specific conditions. Current observational evidence supports dark energy acting similarly to a cosmological constant, where the parameter W is close to -1 but not less than -1. Continued observations, particularly of the universe's expansion rate and the behavior of dark energy, are crucial in determining whether the Big Rip is a plausible future outcome. In the absence of conclusive evidence for W being less than -1, the Big Rip remains one of several theoretical possibilities. Future advancements in astrophysical observations, such as those facilitated by next-generation telescopes and deeper investigations into the nature of dark energy, may provide more clarity on this issue. For now, the Big Rip serves as a fascinating, albeit speculative concept, illustrating the profound influence dark energy could have on the ultimate fate of the universe. The theoretical decay of protons, if it occurs, would have profound implications for the very long-term future of matter in the universe. Proton decay is predicted by certain grand unified theories in particle physics, which aim to unify the fundamental forces of nature. While protons are considered stable in our current observations, some theories suggest they could decay over extremely long timescales, far longer than the current age of the universe. If proton decay is real, it means that even the most stable forms of matter are not eternal. The implications for the far future of the universe would be profound. First, the decay of protons and neutrons, which are the building blocks of atomic nuclei, would lead to the gradual decay of all baryonic matter. This includes the nuclei of atoms, and over incredibly long timescales, all normal matter, stars, planets, and remnants like white dwarfs and neutron stars would eventually decay into lighter particles such as positrons, neutrinos, and photons, depending on the specific decay channels. In this scenario, even stellar remnants would not be spared. White dwarfs and neutron stars, which currently are expected to last for eons, would eventually dissipate as their constituent protons and neutrons decay, turning them into a mix of radiation and lighter particles. As protons decay, atoms would no longer be able to hold together, causing molecules to dissociate and chemical bonds to fail. This would result in material objects losing their structural integrity and disintegrating into a diffuse collection of subatomic particles. Following the decay of all matter, the universe would enter a dark era, dominated by radiation and particle remnants from proton decay. Only black holes would remain as significant structures, but even they are not immune to eventual decay through Hawking radiation. Over timescales far exceeding 10 circumflex 100 years, black holes would gradually lose mass due to Hawking radiation, eventually evaporating completely. This process would leave the universe sparsely populated with elementary particles and low-energy photons. The end state of proton decay would contribute to the heat death of the universe. As all structures decay and radiation spreads out uniformly, the universe would approach a state of maximum entropy, a thermodynamic equilibrium where no useful energy remains to do work. In this scenario, the universe would become a cold, inert space filled with a dilute gas of fundamental particles and radiation. The potential for proton decay illustrates a universe in constant evolution, moving towards thermodynamic equilibrium. Although proton decay has not yet been observed, understanding this process remains a key goal in theoretical physics. It highlights the temporality of all structures in the universe and aligns with the broader view of a cosmos in perpetual flux. The theoretical heat death, also known as the Big Freeze, represents a possible ultimate fate of the cosmos. It is characterized by a state of maximum entropy, where all thermodynamic processes cease. This concept is grounded in the second law of thermodynamics, which posits that the total entropy of a closed system will tend to increase over time until it reaches equilibrium. If the universe were to undergo heat death, several significant consequences would unfold over incredibly long timescales. First, star formation would cease as the universe expands and galaxies drift further apart, leading to a gradual dimming of the cosmos. Existing stars would exhaust their nuclear fuel, transitioning to white dwarfs, neutron stars, or black holes. These remnants would either cool and fade or evaporate over eons. Proton decay would further disintegrate atomic nuclei, turning all baryonic matter into a dilute mix of subatomic particles. Black holes would eventually evaporate through Hawking radiation, leading to a universe filled with low-energy particles and photons. As energy spreads more evenly and structures decay, the cosmic temperature would approach absolute zero, leading to a state where no physical processes can decrease entropy. The universe would become a dark, dilute expanse, with no significant structures or gradients capable of performing work. This heat death scenario emphasizes the ultimate temporality and decay of all cosmic structures. It highlights the inexorable march of entropy and the potential end state of an endlessly expanding universe. The contemplation of heat death serves as a reminder of the vast timescales of cosmological processes and our fleeting existence within a relatively youthful universe. Quantum tunneling and the stability of the vacuum are intriguing subjects with profound implications for the far future of the universe. In quantum field theory, the vacuum is not merely empty space, but a complex state characterized by certain energy fields. The conceptual stability of this vacuum state is essential for the continued existence of the universe as we know it. One key idea linked to quantum tunneling and vacuum stability is the possibility of false vacuum decay. Our universe might currently reside in a false vacuum, a metastable state with higher energy compared to a more stable, true vacuum. Due to quantum tunneling, a region of the false vacuum could spontaneously transition into the true vacuum state. If such a tunneling event occurs, it would create a bubble of true vacuum that expands at the speed of light. Inside this bubble, the laws of physics and fundamental constants might be drastically different. This bubble would rapidly grow, converting the false vacuum state universe into the true vacuum state, erasing existing structures and potentially ending all forms of life and matter as we understand them. The probability of such a vacuum decay event is determined by factors including the energy barrier between the false vacuum and the true vacuum states. Despite being conceptually possible, current estimates suggest that such an event would be exceedingly rare over even cosmological timescales. The possibility of false vacuum decay raises interesting questions about the ultimate fate of the universe. Although current models suggest the universe is stable for the foreseeable future, the theoretical underpinning implies that we live in a fundamentally unstable environment on the longest timescales. Quantum tunneling could hypothetically affect the long-term stability of the vacuum by triggering a transition from a false vacuum to a true vacuum state. While such an event is not expected to occur soon, its implications underscore the intricacies and uncertainties inherent in our understanding of the universe. This concept continues to spark significant theoretical exploration, emphasizing both the fragility and complexity of the vacuum state and the far-reaching consequences of quantum mechanics. The long-term fate of information in a universe dominated by black holes is deeply connected to the principles of quantum mechanics, thermodynamics, and the nature of black holes themselves. This topic has generated significant debate and research, particularly revolving around the information paradox. The information paradox arises because, according to classical interpretations of black holes, any information about matter that falls into a black hole seems to be lost from the observable universe once it passes the event horizon. However, this contradicts quantum mechanics, which states that information cannot be destroyed. Stephen Hawking initially suggested that black holes radiate away information through Hawking radiation, leading to the possibility that information might be lost forever once a black hole evaporates completely. Over incredibly long timescales, black holes emit Hawking radiation, gradually losing mass and energy until they theoretically evaporate entirely. If information stored within the black hole were genuinely lost, it would imply a violation of the conservation of information, a cornerstone of quantum theory. Several theories have been proposed to resolve the information paradox. One idea is that information is encoded in the Hawking radiation itself, though the mechanism remains unclear. Another hypothesis is the holographic principle, suggesting that all information about the interior of a black hole is encoded on its event horizon, supporting the idea that information is preserved and can be recovered. In a universe dominated by black holes emitting Hawking radiation, the eventual evaporation of all black holes would lead to a state where the universe becomes a sparse, cold expanse filled with low-energy photons and fundamental particles. The ultimate fate of information would depend on the interplay between information preservation principles and the dispersal of these particles. Following the extensive evaporation of black holes, the universe would approach heat death, a state of maximum entropy where no thermodynamic processes can occur, and all matter is in thermal equilibrium. In this state, information might still be encoded in the fluctuations of the remaining low-energy particles, though it would be practically unrecoverable. In conclusion, the long-term fate of information in a universe dominated by black holes hinges on resolving the information paradox. Current theoretical models suggest that information might be preserved in subtle ways that we do not yet fully understand. While these resolutions offer hope that information is never truly lost, the practical recovery of such information in an increasingly sparse and cold universe would be an immense challenge, pushing the boundaries of our understanding of fundamental physics. The influence of intelligent life on the long-term evolution of the cosmos is a fascinating and highly speculative topic, with profound implications for the future of the universe. Given the vast timescales involved, the potential actions of advanced civilizations could significantly shape cosmic phenomena. Advanced civilizations are classified using the Kardashev scale, which measures energy consumption. Type 1 civilizations harness all the energy available on their home planet. Type 2 civilizations utilize the energy of their entire star, for example, through Dyson spheres. Type 3 civilizations control energy on the scale of their entire galaxy. If intelligent life evolves to become Type 2 or Type 3, their manipulation of energy sources could dramatically alter celestial objects and processes. For example, constructing Dyson spheres around stars might change the star's emission properties, lifespan, and evolution. Large-scale engineering projects of a Type 3 civilization might reshape galaxies by rerouting interstellar gas, modifying star formation rates, or even moving stars to optimize energy collection or avoid hazardous regions. Advanced civilizations could engage in stellar engineering, modifying stars to extend their lifetimes or increase their energy output. This might involve adding mass to smaller stars to transform them into larger, longer-lived ones, or siphoning mass from giants to form new stars, creating stable, long-lived energy sources to sustain technological activities. As the long-term habitable conditions change due to natural cosmic evolution, intelligent life might implement preservation strategies or migrate to more suitable environments. Directed panspermia, or the intentional spreading of life to habitable exoplanets, can ensure the continuation of life across the universe. Dyson spheres or habitats around long-lived stars, brown dwarfs, or even rogue planets could provide stable refuges for civilization. Advanced civilizations might also attempt to influence cosmic events perceived as threats. By manipulating black holes and their Hawking radiation, they could theoretically slow down their evaporation or extract energy more efficiently. They might also encourage or reconstruct planetary and stellar systems in stable configurations to prevent collisions or destructive events. The far future influence of intelligent life might revolve around highly sophisticated computational technologies. Utilizing remaining energy sources for vast computation purposes, simulating other universes or creating artificial environments could be key. Engaging in digital consciousness, where civilizations preserve information and consciousness through computation in low-energy states as the universe cools and approaches heat death, is another possibility. Speculatively, advanced theoretical physics might offer means to counteract heat death or explore alternate universes via mechanisms such as wormholes or manipulating space-time. Knowledge integration might uncover methods to stabilize vacuum states, seed new universes with favorable conditions, or evade cosmic end states. In an accelerating universe driven by dark energy, intelligent life might develop strategies to counteract isolation. Creating networks of communication, energy transfer, or matter exchange over astronomical distances to sustain interconnected civilizations could be a solution. The potential actions of intelligent life on the universe's fate span from energy harvesting and stellar manipulation to more wild theoretical constructs involving alternate universes or countering entropy. While these scenarios remain speculative, they invite contemplation on the intersection of intelligence, technological advancement, and cosmic destiny, pushing our understanding of the universe and our place within it to extraordinary heights.